Let's begin by considering the ground right outside your window. To our eyes and beneath our feet, the Earth feels like the very definition of permanence. We build our homes on it, we pave long highways across it, and we trust, implicitly, that the landscape we wake up to today will be exactly the same landscape we see tomorrow. A mountain in the distance looks like a static monument, frozen in place since the dawn of the world. A canyon seems like a massive void that has simply always been there. But this feeling of stillness is merely an illusion, a gentle trick played on us by the limits of our own perception. The Earth is not a static rock. It is a restless, breathing, dynamic system. It is constantly shifting, cracking, folding, and remaking itself. The only reason it feels perfectly still is that the Earth moves at a pace that our minds are simply not designed to register. To understand geology, we have to stretch our imagination and step outside the familiar, hurried rhythm of human time. Think about how we measure our lives. We break our days into hours and minutes, dictated by the spinning of the planet and the immediate demands of our schedules. We think in terms of weeks, seasons, the duration of a 30-year mortgage, or the span of a career. A century feels like an incredibly long time to us. It encompasses generations, the rise and fall of technologies, the entirety of a long human life. But to the Earth, a century is not even a passing second. It is barely a blink. Geologists use a concept called deep time. Deep time is the vast, almost incomprehensible ocean of history that stretches back billions of years. Imagine, for a moment, the concept of compound interest. In finance, a tiny percentage of growth, left alone, doesn't seem to do much in a month or a year. The daily change is invisible. But over decades, that tiny, silent accumulation snowballs into massive, undeniable results. Deep time operates on exactly the same principle, but the currency is physical change. A single speck of dust settling on a lake bed, a microscopic layer of stone worn away by the wind, a fraction of a millimeter of rock pushed upward by forces deep below, these physical events are completely invisible on a Tuesday afternoon. But multiply that fraction of a millimeter by 10 million years, and you have built the towering, snow-capped peaks of the Himalayas. Multiply that single grain of sand by 100 million years, and you have filled an entire ocean basin, creating the bedrock for a future continent. When we view the world through the lens of deep time, the impossible becomes inevitable. Let us try to picture this vast scale together. Imagine you had a magical camera, one that you could set on a sturdy tripod and leave running not for a fraction of a second, but for 100 million years, capturing a long-exposure photograph of the Earth. If you could watch that recording playback in just a few minutes, the solid, unyielding world you know would completely disappear. You would see that the ground is actually a fluid, restless surface. You would watch oceans slowly open up like vast blue flowers, and then slowly close again as continents drift together to form new, massive puzzles of land. You would see solid rock folding and bending like warm wax under the immense pressure of tectonic collisions. You would watch towering mountain ranges ripple upward like slow-motion waves on a vast ocean, only to be gradually worn back down to flat plains by the persistent, sweeping hands of rain and wind. The surface of our planet would look like a living, breathing canvas, constantly being erased and painted over again. This is the quiet pulse of the Earth. It is a rhythm so slow, so steady, and so deeply patient that it surrounds us without ever disturbing our peace. You can actually see the evidence of this deep, patient time in the world around you if you simply know how to look for it. Think of an old stone staircase in a historic building, perhaps a cathedral or a grand train station that has been heavily used for hundreds of years. If you look closely at the center of the steps, you will see a gentle, smooth dip in the stone. That dip wasn't carved by a heavy chisel. It was carved by the soft soles of millions of leather and rubber shoes, walking up and down, day after day, year after year. Every single footstep removed an invisible, microscopic layer of stone. No one walking up those stairs ever felt the rock yield beneath them. But the cumulative power of those tiny interactions, repeated over centuries, effortlessly reshaped solid granite. The earth shapes itself in the exact same way, just on a canvas that is infinitely larger. The water flowing in a gentle stream behind a house is carrying away microscopic particles of sediment, slowly, persistently, carving its way down to the sea. The massive tectonic plates beneath our continents are drifting at about the same speed that your fingernails grow. If you sit perfectly still, you cannot feel your fingernails growing. It is a biological process that happens entirely below the threshold of your awareness. And yet, if you never trimmed them, you would clearly see the undeniable results of that quiet, continuous forward motion. The solid plates of the earth are doing the exact same thing. They are moving right now, creeping along at an incredibly slow, deliberate pace, carrying the weight of entire continents, silent forests, bustling cities, and deep oceans on their backs. There is something deeply comforting about this realization. In our daily lives, we are often caught up in a whirlwind of immediate concerns: the rush of the morning commute, the glowing screens, the urgent tasks, and the frantic pace of the modern world. Everything feels fast, pressing, and fleeting. But when you lie back and consider the earth, you are tuning into a completely different frequency. You are resting on a massive structure that has endured for billions of years, a world that absolutely refuses to be hurried. It does not care about deadlines or schedules. It operates with a grand, majestic patience. Whenever you feel overwhelmed by the speed of life, you can simply close your eyes and remember the deep time happening quietly right beneath you. You are held by a planet that is slowly, calmly, and tirelessly reshaping itself in a beautiful, endless dance. It is a solid foundation built not on stillness, but on perfect, balanced, continuous motion. And with that vast expanse of time stretching out before us, with our minds quieted by the slow, reassuring rhythm of the stone, we are naturally led to ask what lies beneath the surface we rest upon, fueling this ancient, endless movement. Let's set the surface aside for a moment and journey inward. We have spent time thinking about the vast, stretching plains of time, but now we must turn our attention to the vastness of depth. I want you to picture yourself standing outside, feeling the solid ground beneath your shoes. From this vantage point, looking down, the earth feels infinitely deep, an impenetrable block of stone and soil. But if we could somehow peel back the surface, if we could gently slice the planet in half like a piece of fruit, we would see that the earth is not a single, uniform sphere. It is beautifully and neatly divided into distinct layers, each with its own character, its own temperature, and its own vital role in keeping the world above alive. To begin our descent, we first have to understand just how little of the earth we have actually touched. It is a humbling thought to realize that every single human experience, every towering skyscraper, every deep subway tunnel, every sprawling root system of the oldest forests, and even the darkest, most unfathomable trenches of the ocean floor, exists entirely on the very outer skin of the planet. We call this skin the crust. If you were to imagine the earth as a large apple, the crust would be roughly the thickness of the apple's skin. It is remarkably thin, delicate, and brittle compared to the massive bulk of the world that rests beneath it. Even our most ambitious attempts to dig down into the earth have barely scratched this surface. Decades ago, scientists in Russia set out to drill as far down as their technology would allow. They spent years grinding through solid rock, eventually reaching a depth of just over 7 miles. To us, 7 miles straight down sounds like a staggering distance. But, in the grand scale of the earth, which is nearly 4,000 miles from the surface to the center. That 7-mile hole is little more than a microscopic pinprick. The drill was eventually stopped because the rock became too incredibly hot and malleable, behaving more like warm plastic than solid stone. That is as far as humanity has ever reached. Since we cannot physically travel down into the depths, you might naturally wonder how we know what lies beneath us. The answer is found in the quiet science of listening. Imagine walking up to a large closed wooden door and knocking on it. By the sound it makes, you can easily tell if the door is hollow or completely solid. The sound waves travel differently through empty space than they do through dense wood. Geologists do the exact same thing with the Earth, but instead of knocking, they listen to the deep, low rumbling waves created by earthquakes. When an earthquake happens, it sends waves of energy echoing completely through the planet. As these waves travel downward, they speed up, slow down, or bend depending on what kind of material they are passing through. By measuring these gentle planetary vibrations from all over the world, we have been able to map the deep interior in astonishing detail, entirely by listening to the way the Earth rings like a massive, complex bell. Through this listening, we learned that the crust itself comes in two different varieties. The ground you and I live on, the continental crust, is made mostly of lighter rocks, similar to granite. It is thick, sometimes plunging 20 or 30 miles down, but it is relatively buoyant. The other type of crust lies beneath the oceans. Oceanic crust is much thinner, only a few miles thick, but it is made of dark, heavy, incredibly dense rock called basalt. Because it is so heavy, the oceanic crust sits lower, creating the deep basins that hold the world's oceans. You can imagine a thick block of light wood and a thin block of heavy, dense metal floating side by side in a pool of water. One rides high, holding the continents up into the sky, while the other sinks low, cradling the seas. But eventually, whether you are drifting down through the thick granite of the mountains or the dense basalt of the ocean floor, the crust comes to an end. You cross an invisible boundary, a line where the rock suddenly becomes much denser and the character of the Earth changes entirely. Beneath this boundary lies the mantle. When you think of the mantle, I want you to picture the true bulk of our planet. This single, massive layer extends almost 2,000 miles deep and makes up 84% of the Earth's entire volume. It is the thick, heavy flesh of the apple. There is a common misconception that because it is so incredibly hot down there, the mantle must be a churning ocean of liquid fire and magma. But that is not true. The mantle is solid rock. However, it is a kind of solid rock that we never experience on the cool surface. To understand the mantle, we have to imagine how materials behave when they are pushed to their absolute limits. As you descend into the mantle, the temperature rises to thousands of degrees, but at the same time, the pressure from the millions of tons of rock resting above you becomes absolutely crushing. This immense pressure squeezes the atoms of the rock together so tightly that they cannot melt into a liquid, even though the heat is more than high enough to turn surface rocks into glowing lava. Trapped in this agonizing balance between intense heat trying to melt it and intense pressure forcing it to stay solid, the rock of the mantle adopts a strange, patient compromise. It becomes a flexible solid. Think of a piece of hard wax from a candle. If you hit it with a hammer, it shatters like glass. But if you hold that wax in your warm hands for an hour, applying slow, gentle pressure, you can bend it without breaking it. The mantle behaves exactly like this, but on a scale of millions of years. It is rock that flows. It is a slow, heavy, silent movement, creeping along at the pace of a growing fingernail. Yet it has enough power to carry the continents on its back. As we drift even deeper, moving past the halfway point to the center of the Earth, the mantle grows hotter and the pressure continues to compound. The colors of the rock, if we could see them, would glow with an unimaginable intensity, radiating a fierce, silent heat. We are entering the deepest reaches of the planet's interior, a place where the familiar rules of stone are about to be rewritten. The crushing weight of the world above is now nearly absolute, and the environment is preparing to change drastically one final time. We have reached the very bottom of the rocky mantle, standing on the precipice of something entirely different. The rock is about to fall away, giving way to an ocean of heavy, liquid metal, leading us naturally into the fiery, solid heart of our world. As we drift deeper still, leaving the dense, flexible rock of the lower mantle far behind, we arrive at one of the most profound boundaries on our entire planet. Imagine descending nearly 2,000 miles beneath the familiar surface, sinking through layers of heated stone. Down here, the environment changes with a sudden, beautiful drama. We are no longer dealing with rock. The heavy, pressurized stone falls away entirely, and we are met instead with a boundless, churning ocean of liquid metal. This is the beginning of the outer core. It is a vast, subterranean world composed almost entirely of iron and nickel, glowing with a fierce, brilliant white heat. If you were to somehow stand on the edge of the mantle and look down into this space, you would not see the steady, slow creep of solid stone, but rather a fluid, dynamic sea of molten iron, turning and flowing in the absolute dark. To understand the nature of this liquid ocean, we have to imagine the sheer scale of the heat involved. The temperature in the outer core is staggering, reaching thousands upon thousands of degrees, easily rivaling the intense fires found on the surface of the sun. At these temperatures, the iron and nickel have completely melted, losing all the rigid structure of a solid. But unlike a peaceful, still lake on a quiet summer evening, this ocean of metal is in constant, swirling motion. The heat from the very center of the Earth rises up, warming the liquid metal at the bottom of the outer core, causing it to become lighter and gently float upward. As it nears the cooler rock of the mantle above, it loses some of its heat, becomes heavy again, and sinks back down into the depths. This is a massive, slow-rolling boil, an endless cycle of rising and falling heat hidden deep beneath our feet. But this liquid metal isn't just rising and sinking, it is also being swept up in the rotation of the planet itself. As the Earth spins through space, day after day, year after year, it drags this massive ocean of molten iron along with it. The spinning of the Earth causes the rising and falling columns of liquid metal to twist and spiral, like massive, slow-moving tornadoes of glowing iron. And when you have an ocean of electrically conductive metal moving and twisting on such a colossal scale, something truly magical happens. It acts like an enormous, self-sustaining generator. The swirling, flowing iron creates electrical currents, and these currents, in turn, generate a massive magnetic field that reaches far beyond the liquid metal itself. We call this beautiful, unseen engine a geodynamo. You cannot see this magnetic field, nor can you hear it or feel it as you walk down the street or drive in your car. It is completely silent and entirely invisible to our senses. Yet, it reaches up through the thick mantle, up through the brittle crust, out into the open air, and extends thousands of miles into the freezing vacuum of space. It forms a massive, invisible shield, a protective bubble wrapped safely around our entire planet. When you hold a simple compass in your hand and watch the needle gently swing to point north, you are actually watching a tiny piece of metal aligning itself with the vast, twisting ocean of liquid iron thousands of miles beneath you. The compass is a direct, quiet connection between the palm of your hand and the glowing heart of the Earth. This invisible shield is not just a geological curiosity, it is the very reason we can live peacefully on the surface. Our sun is constantly releasing a harsh, invisible storm of energy and radiation known as the solar wind. Without our magnetic shield, this solar wind would relentlessly strip away our delicate atmosphere, leaving the Earth bare and lifeless. But because of the churning iron core, the solar wind hits our magnetic field and is gracefully deflected away, washing harmlessly around our planet like river water flowing around a smooth, submerged stone. The only time we ever get to see this invisible shield at work is near the North and South poles. Sometimes, a tiny bit of the sun's energy slides down the magnetic lines and interacts with the gases in our upper atmosphere, creating the breathtaking, shimmering curtains of green and purple light we call the aurora borealis, or the northern lights. That silent, slow-moving light show in the night sky is the visible signature of the molten iron ocean deep below, quietly keeping us safe as we sleep. But this liquid ocean is only the outer layer of the Earth's heart. Let us leave the swirling currents behind and drift even closer to the very center of the planet. As we push through the liquid iron and descend the final few hundred miles, the pressure continues to mount. The heat grows even more intense, but the pressure here is the true master. You are now feeling the combined weight of the entire planet, every mountain range, every deep ocean basin, every sprawling continent, and thousands of miles of heavy rock and molten metal pressing down on a single central point. The pressure is millions of times greater than the gentle air pressure you feel standing on a beach, and this unimaginably heavy embrace forces the Earth to do something incredible. We finally arrive at the inner core. It is a perfect, glowing sphere, roughly the size of our moon, suspended in the exact center of the Earth. Like the outer core, it is made almost entirely of pure iron and nickel. It is the hottest place on the planet, radiating heat that matches the blazing, volatile surface of a star. By all logic, it should be a chaotic, boiling liquid, or even a gas. But because the pressure from the rest of the world pressing in on it is so absolute, the atoms of iron are completely trapped. They are squeezed together so tightly, packed so densely into a fixed geometric grid that they cannot move, they cannot flow, they cannot melt. The intense pressure forces the glowing iron to become a beautiful, solid crystal. Picture this magnificent, silent anchor at the center of the world. It is a blindingly hot, solid iron moon, entombed in an ocean of liquid metal, completely hidden from the light of day. While the surface of the Earth experiences raging storms, the slow drifting of continents, and the passing of countless seasons, the inner core remains steadfast. It does not churn or boil. It simply hums with heat and pressure. Curiously, scientists have discovered through their deep listening that this solid iron sphere is not completely locked to the rest of the planet. Because it sits suspended in its liquid casing, it actually spins independently. It rotates just a fraction of a degree faster than the rock and crust above it, turning silently, patiently, at its own majestic pace in the deep dark. This massive, solid iron heart is the great furnace of the Earth. As it slowly, imperceptibly cools over billions of years, it releases its deep, primordial heat outward. That heat travels up through the churning liquid of the outer core, and it presses against the solid, heavy rock of the mantle above it. This slow, steady release of energy from the center of the world is the engine that drives everything we see on the surface. It is a chain reaction of warmth and movement, beginning at the very center and rippling outward to shape our mountains and oceans. Knowing that this brilliant, unseen engine is quietly running beneath us, pushing its heat upward in the dark, we might wonder what it does to the thick, flexible layers of rock resting gently just above it. Knowing that this brilliant, unseen engine is quietly running beneath us, pushing its heat upward in the dark, we might naturally wonder what it does to the thick, flexible layers of rock resting gently just above it. We have just left the brilliant, glowing ocean of liquid iron that makes up the outer core, a place of intense, fluid motion. Now, as we begin to rise back toward the surface, we cross a distinct threshold. The liquid metal gives way, and we find ourselves at the very bottom of the mantle. This is the great interior bulk of our world. If the Earth were a heavy, ripe peach, the mantle would be the thick, dense flesh that makes up almost everything between the pit and the skin. It is an unimaginably vast layer, stretching for nearly 2,000 miles from its bottom edge right up to the thin, cool crust we live on. When we think of the inside of the Earth, popular imagination often paints a picture of a hollow world, or perhaps an endless, churning sea of liquid orange magma just waiting to erupt. But as we drift through the mantle, we find that this simply isn't true. The mantle is composed of solid rock. If you could somehow bring a piece of it up to the surface and cool it down, it would look like a heavy, dense, dark green stone. However, the rock down here does not behave like the stone we know on the surface. It is trapped in a beautiful, agonizing balance between two overwhelming forces: the blinding heat rising from the core and the crushing weight of the world pressing down from above. To understand how rock behaves in this deep, hidden place, we can think about a familiar experience from a hot summer day. Imagine a freshly paved asphalt road. In the dead of winter, when the air is freezing, that asphalt is completely rigid. It is hard, brittle, and if you were to strike it with a heavy hammer, it would chip and shatter into sharp pieces. But think about that same road in the middle of July, baking under the afternoon sun for days on end. The heat sinks into the black pavement. If a heavy delivery truck parks on that road and sits there for a few hours, the asphalt doesn't melt into a puddle of liquid. It remains completely solid. Yet, when the truck finally pulls away, you can see the shallow, smooth indentations where the heavy tires rested. The solid road yielded to the pressure and the heat. It deformed. It flowed. The rock of the entire mantle behaves in exactly this same way, but on a scale that humbles the mind. It is a solid that flows. Because it is so incredibly hot, yet squeezed so tightly that it cannot melt, the rock becomes viscous, like thick, warm caramel, or a dense piece of taffy left in a warm room. It is fully solid, yet over the course of millions of years, it bends, it stretches, and it creeps. This slow, majestic movement is the heartbeat of the planet, a process that geologists call convection. You might already be intimately familiar with the concept of convection, even if you've never used the word. If you live in a house with a radiator or a baseboard heater, you know exactly how this works. On a cold winter evening, the heater warms the air immediately around it. Because warm air is lighter and less dense than cold air, it slowly rises to the ceiling. It gently drifts across the room, gradually losing its heat to the cold windows and the walls. As it cools, it becomes heavier, and it slowly sinks down the opposite wall to the floor, where it is eventually drawn back toward the heater to be warmed all over again. It is a continuous, invisible loop of warming, rising, cooling, and sinking. Now, picture this exact same continuous loop, not with invisible air in a quiet living room, but with billions of tons of solid rock deep inside the earth. The solid iron core acts just like the heater in your home. It relentlessly bakes the very bottom layer of the mantle. Over tens of thousands of years, this deep rock absorbs the heat. It expands ever so slightly. It becomes just a fraction less dense than the cooler rock resting heavily above it. And because it is lighter, it begins to rise. Imagine a massive column of hot, solid stone, perhaps hundreds of miles wide, slowly pushing its way upward toward the surface. It is a buoyant plume of deep earth, rising with the deliberate, unstoppable slowness of a growing oak tree. It moves only a few inches every single year. A human observer standing beside it would see absolutely no motion at all. It is a journey of supreme patience. It takes millions upon millions of years for this rising column of heated rock to travel from the deep boundary of the core all the way up to the uppermost reaches of the mantle. Eventually, this rising plume approaches the very top of the mantle, right just below the crust of the earth. But it cannot break through the hard, rigid shell of the surface. So, just like the warm air hitting the ceiling of your living room, the flowing rock spreads out. It gently flattens and pushes outward, sliding horizontally directly beneath the crust. As it slides along in the dark, it is finally far enough away from the furnace of the core to begin losing its heat. The chill of the surface above seeps down into the rock. The stone begins to cool. As it cools, it gently contracts. It grows denser, heavier, and more sluggish. After millions of years of horizontal travel, it finally becomes so heavy that it can no longer stay afloat in the upper mantle. Slowly, silently, the cold, heavy rock begins to sink. It falls back down into the abyss, descending mile after mile, century after century, returning to the deep, fiery boundary of the core, where it will eventually be warmed and begin the majestic journey all over again. This vast, rolling movement is the slow dance of the mantle. It is a cycle of beautiful, endless breathing, operating entirely outside the realm of human time. There are massive, slow-rolling convection currents turning quietly beneath the oceans and the continents right now as you rest. It is a comforting thought to realize that the deep earth is not stagnant or dead, but is actively circulating, turning itself over in a slow, peaceful rhythm that has continued unbroken since the planet was formed. But this peaceful movement in the deep does not happen in isolation. It has profound, undeniable consequences for the world above. As these massive currents of solid rock rise, spread out, and slide horizontally beneath the Earth's surface, they create an immense amount of friction against the bottom of the crust. Imagine a slow, heavy river of ice drifting just beneath a wooden raft. Even if the river is moving at only a creeping pace, its sheer mass and friction will eventually begin to drag the raft along with it. The mantle, dragging against the underside of the Earth's crust, creates a slow, relentless, pulling force. It is the engine that drives everything we see on a map. This friction is what pulls continents apart, what pushes mountain ranges into the clouds, and what slowly rearranges the face of the globe over millions of years. And as this massive layer of hot rock slowly rolls and breathes, it carries the thin, brittle skin of the Earth along with it. This gentle but unstoppable pulling leads us softly away from the deep, flowing rock and upward to the cool, fragmented surface we call home, where the solid ground is about to break. Let's pick up that thread right where we left it, rising gently from the deep, flowing rock of the mantle and arriving back at the cool, fragmented surface we call home. We have spent our time thus far in a world defined by crushing pressure and unimaginable heat, a place where solid rock is forced to bend and creep like warm taffy in the dark. But as we move away from the glowing furnace of the core, rising mile after mile, the temperature steadily begins to fall. The deep, primordial heat of the Earth struggles to reach this far up, and the freezing, empty void of space begins to exert its quiet influence from above. Here, at the very outer edge of the planet, the rules of the deep are suddenly and beautifully abandoned. The rock loses its flexibility. It cools, it stiffens, and it locks into place, creating a rigid, unyielding layer that geologists call the lithosphere. When we think of the ground beneath us, we usually just picture the crust, that delicate, paper-thin skin of rock and soil that holds our oceans, our forests, and our cities. But the lithosphere is actually a bit thicker and a bit more complex than just the crust alone. Imagine a vast, deep lake in the dead of winter. The water deep down remains fluid, moving in slow, silent currents, protected from the cold. But the water at the very top, directly exposed to the freezing winter air, turns into a thick, hard layer of ice. The lithosphere is very much like that layer of winter ice. It is made up of the crust, yes, but it also includes the very topmost portion of the mantle, a layer of stone that has cooled down so much that it can no longer bend or flow. Together, the crust and this frozen top layer of the mantle fuse into one solid, brittle shell that wraps entirely around the globe. To truly understand the nature of this shell, we must focus gently on that word, brittle. In our everyday lives, we are surrounded by things that are brittle. Think of a pane of window glass, a ceramic coffee mug resting on a table, or a dry branch snapped underfoot in the woods. When you apply pressure to something brittle, it does not bend and it does not stretch. For a long while, it simply resists. It holds its shape perfectly, absorbing the stress in total silence. But eventually, if the pressure continues to build without relief, the material reaches its breaking point. It doesn't yield gracefully, it snaps. This is the fundamental defining difference between the deep Earth and the surface. Down in the heated depths, the planet bends. Up here in the cold lithosphere, the planet breaks. Because of this rigid, brittle nature, the lithosphere is not one perfectly smooth, unbroken sphere. The slow, relentless dragging of the flowing mantle beneath it, that massive, sluggish river of hot rock we explored just a moment ago, places an incredible amount of stress on the cold shell above. Over millions of years, the shell simply couldn't withstand the tension of being pulled in so many different directions. Long ago, the strain became too much, and the shell cracked. Imagine taking a perfectly hard-boiled egg and tapping it gently on a kitchen counter, striking it just hard enough to fracture the shell into a dozen large, interlocking fragments. If you look closely at the egg as it rests in your hand, the shell is still entirely there, wrapping the soft center completely. But it is now divided by a network of deep, jagged cracks. This is exactly what the surface of the Earth looks like. The lithosphere is shattered into massive, irregular slabs of solid rock, which we call tectonic plates. There are about 7 or 8 primary plates, along with dozens of smaller, supporting ones, and they fit together snugly, exactly like the pieces of a massive, spherical jigsaw puzzle. The scale of these plates is almost beyond human comprehension. A single plate is not just a mountain, or a state, or even a country. A single tectonic plate can be millions of square miles in size. The North American plate, for instance, carries not only the entire continent of North America, from the warm, sunlit beaches of Mexico to the frozen tundra of northern Canada, but it also reaches far out into the sea, carrying half of the Atlantic Ocean, all resting on one single, unbroken slab of rock. These plates also come in 2 distinct varieties, bringing a beautiful imbalance to the puzzle. Some plates are made mostly of continental crust, which is very thick but surprisingly lightweight, like a massive block of styrofoam. Other plates are made mostly of oceanic crust, which is much thinner but incredibly dense and heavy, like a sheet of solid iron. This difference in weight and thickness is what gives our world its varied landscape, pushing some areas high into the sky and allowing others to sink low enough to cradle the world's oceans. It is a strange and deeply humbling realization to know that the solid ground we build our lives upon, the foundation we trust so implicitly, is actually just a fractured piece of a larger, broken shell. But if these massive plates of rock are heavily broken, why don't they sink? Why don't they tumble down into the hot, chaotic depths of the Earth? The answer lies in the specific texture of the layer resting immediately below them. Just beneath the brittle, rigid rock of the lithosphere is a slightly warmer, slightly softer layer of the upper mantle. It is completely solid, but just soft enough to be pliable like a dense, heavy, supportive cushion. The tectonic plates do not sink because they are literally floating on this dense, pliable cushion, just as heavy steel barges manage to float effortlessly on the surface of a deep, slow-moving river. The heavy plates press down into the soft rock, finding a perfect, natural buoyancy. Because they are floating, and because they are not permanently anchored to the soft rock below, these massive puzzle pieces are completely free to move. The slow, rolling convection currents deep within the mantle act like giant, silent conveyor belts, gently dragging the plates along for the ride. They move at a glacial pace, creeping along at perhaps an inch or 2 a single year. It is a movement so incredibly gradual, so deeply peaceful in its slowness, that you can sit in a quiet room or lie still in your bed for a lifetime and never once feel the ground travel beneath you. The world feels perfectly still. Yet, despite this profound, comforting stillness, the implications of this quiet movement are staggering. Given enough time, the vast, deep ocean of time we spoke of when we began our journey, a journey of an inch a year, can transport an entire continent across the globe. It can slowly tear ancient landmasses apart and slam vast oceans shut. It shifts the climate, it gently alters the paths of deep ocean currents, and it dictates the rise and fall of every mountain range on the planet. The Earth is a beautiful, restless puzzle, and its pieces are always quietly in motion. Let us take a moment to set that idea down now, fully formed, and let our attention drift naturally toward what that slow, endless journey looks like, imagining how the familiar map of our world was drawn as we watch these great continents drift across the seafloor. Let us let our attention drift naturally toward what that slow, endless journey actually looks like, imagining how the familiar map of our world was drawn as we watch these great continents drift across the seafloor. I want you to picture a globe in your mind, or perhaps a flat map of the world that you might have pinned to a wall at some point in your life. We are so deeply accustomed to the shapes of the land masses. We know the recognizable curve of the eastern seaboard of the United States, the tapering tip of South America, the vast, bulky shoulder of Africa, and the isolated expanse of Australia. We take these shapes and their exact distances from one another as permanent geographical facts. We build our entire sense of global navigation and geography on the assumption that this map is final. But remember the deep, expansive ocean of time we stepped into at the very beginning of our journey. If we view the map through the lens of deep time, we realize that the globe we recognize today is nothing more than a single, fleeting snapshot. It is just one frame in a beautiful, slow-motion film that has been running for billions of years. You might already have a sense of this restless geography just from looking at the shapes of the continents. If you bring to mind the eastern coastline of South America and the western coastline of Africa, you can clearly see how they seem to mirror one another. They look exactly like two adjacent pieces of a massive jigsaw puzzle. This is not a new observation. People noticed it centuries ago, as soon as the first accurate maps of the oceans were drawn. For a long time, it was casually dismissed as a charming coincidence. The idea that entire continents, billions of tons of solid rock, could somehow sail across the face of the Earth seemed entirely impossible. But as we began to look closer, the Earth revealed its quiet secrets. When we examine the deep layers of rock on the coast of Brazil, we find that they are an absolutely perfect match for the deep layers of rock on the coast of West Africa. They share the same age, the same mineral composition, and the same distinct sequence of layers. It is as if a single, magnificent painting was torn squarely down the middle, and the two halves were dragged thousands of miles apart. And the evidence goes far beyond just the stone. When we look at the fossils trapped in those rocks, a beautiful, undeniable story emerges. We find the remains of ancient, heavy-set reptiles, animals that could never swim across a vast, turbulent ocean, resting peacefully in the rocks of both continents. We find the delicate, fossilized leaves of the same extinct ferns scattered across South America, Africa, India, Antarctica, and Australia. Imagine finding a torn piece of a handwritten letter on a sidewalk in New York, and then finding the exact matching half of that same letter on a street in London. You wouldn't assume the two pieces were created independently on opposite sides of the ocean. You would know with absolute certainty that they were once joined together in a single place. Let us run the film backward. Let's wind the clock of the Earth back hundreds of millions of years into the past. As we do, the Atlantic Ocean slowly begins to shrink. The Americas drift backward, sliding smoothly toward the east. Europe and Africa drift toward the west. India, which is currently fused to the bottom of Asia, gently detaches and slides southward across the Indian Ocean. If we travel back roughly 250 million years, a time long before the first dinosaurs even walked the Earth, the map looks completely unrecognizable. All the major landmasses on the planet have been slowly pushed together into one single colossal supercontinent. We call this ancient, magnificent island Pangaea, a word that simply means all the Earth. Picture what it would be like to stand in the very center of Pangaea. You would be surrounded by an endless expanse of land in every direction. The nearest ocean might be thousands of miles away. It was a vast, extreme world, surrounded on all sides by one single, continuous, global ocean that wrapped around the rest of the planet. But as we know from our journey into the deep mantle, the Earth is always moving, always breathing with heat. This massive blanket of continental rock acted like an incredibly thick insulator. The intense heat from the core and the churning mantle below began to build up beneath Pangaea. Slowly, the heat caused the rock beneath the supercontinent to expand and dome upward. The land stretched, pulling tighter and tighter, until eventually the cold, brittle shell of the lithosphere could no longer hold. The great landmass began to tear. Imagine a loaf of bread baking in the oven. As the dough inside heats and expands, the rigid, crusty surface of the bread cracks and pulls apart, revealing the softer material beneath. This is precisely how the Atlantic Ocean was born. A long, deep rift valley opened up between the Americas and the combined mass of Europe and Africa. Over millions of years, the rift widened. The low-lying valley eventually filled with water from the surrounding global ocean, creating a narrow, shallow sea that very slowly grew into the vast, deep blue expanse of the Atlantic we know today. And this incredible process of tearing and spreading hasn't stopped. It is happening right now, at this very moment, hidden away in the absolute dark at the bottom of the sea. If we could dive down through the miles of freezing water to the center of the Atlantic Ocean, we would find a massive, underwater mountain range wrapping around the globe like the raised seam on a baseball. This is the Mid-Atlantic Ridge. It is the longest mountain range in the world, and it is entirely submerged. This ridge is the exact place where the tectonic plates are still gently pulling apart. As the plates separate, pulling away from each other like two slow-moving conveyor belts, a gap opens up in the seafloor. But the Earth does not leave empty spaces. Immediately, hot, flexible rock from the mantle rises up to fill the void. As soon as it hits the freezing ocean water, it cools and hardens, creating brand new crust. The Earth is continuously healing its own wound, laying down a fresh strip of volcanic rock, and then immediately splitting that new rock in half and pulling it apart again. This is seafloor spreading. It is a slow, endless engine of creation. Every single year, the conveyor belt of the ocean floor creates about an inch or two of new rock. It is a pace so gentle, so entirely unhurried, that it perfectly matches the speed at which your hair grows. Yet, this quiet, microscopic growth is enough to push massive continents further and further apart. As you rest tonight, as you take your next breath, Europe and North America are a tiny fraction of a millimeter further away from each other than they were when you went to sleep. It is a deeply peaceful thought. The world is carrying us on a majestic, slow-motion voyage across the face of the planet. But the Earth is a sphere, beautifully finite and whole. If new rock is constantly being created in the center of the oceans, pushing the continents apart and making the Atlantic wider, the space must eventually run out somewhere else. The plates cannot simply travel forever without encountering an obstacle. The old crust must be dealt with, and the moving edges of the world must eventually collide. And this natural consequence leads us softly onward to ask what happens when these massive, wandering slabs of stone finally meet one another in the dark. We ended our last exploration with a profound realization. The Earth's surface is constantly in motion. But because our planet is a perfect, finite sphere, the vast tectonic plates cannot simply wander endlessly into empty space. There is only so much room on the surface of the globe. If new rock is continually being born in the deep oceans, pushing the massive continents steadily apart, then somewhere else, the older rock must be making way. The edges of these great, wandering slabs of stone must eventually meet. And it is exactly here, at the quiet, invisible borders where the plates interact, that the true drama and artistry of the Earth's geology unfolds. But remember, in the peaceful realm of deep time, even a collision of continents is a beautifully slow, majestic event. When these giant puzzle pieces of rock interact, they do so in three calm, distinct ways, each sculpting the landscape above in its own unique manner. Let us first imagine a slow-moving highway in your mind. Sometimes plates do not collide at all. Instead, they gently pull away from each other, like two cars side by side naturally drifting into different lanes. We touched upon this briefly when we imagined the mid-Atlantic ridge, hidden deep beneath the ocean, where the seafloor softly spreads. But this gentle pulling apart happens on dry land as well, and it is a breathtaking process to understand. Imagine standing in a vast, wide valley. Beneath your feet, the thick continental crust is being slowly stretched by the churning currents of the mantle far below. The rock resting on the surface is cold and brittle, and as it is pulled horizontally in opposite directions, it begins to thin out. Eventually, the tension becomes too much, and the center of the land simply drops down, forming a massive sunken trench. This is called a rift valley. If you were to travel to East Africa today, you could see this happening right now. The continent is very slowly, over millions of years, tearing itself in two. It is an incredibly peaceful stretching, happening so gradually that the animals, rivers, and forests go about their daily existence completely undisturbed. But deep below, the crust is stretching, fracturing, and the hot mantle is rising to fill the widening gap. Eventually, millions of years from now, that inland valley will stretch so wide and sink so deeply that the salty waters of the Indian Ocean will quietly rush in, creating a brand new sea. The edges of the torn continent will drift apart, becoming the opposite shores of a new world. This pulling away is the first way the Earth accommodates its moving shell, a quiet yielding that creates new space from nothing. But not all plates are moving directly away from each other. Other times, these massive slabs of rock slide directly past one another, grinding horizontally, shoulder to shoulder. Think of two incredibly massive ships brushing against each other in a narrow harbor. They do not crash head-on, nor do they sail apart. They simply scrape heavily along their sides. In geology, this is known as a transform boundary. Because the edges of tectonic plates are not perfectly smooth, they are rough, jagged, heavy expanses of solid stone. They do not glide past one another easily. As the incredibly slow currents in the mantle push one plate north and the neighboring plate south, the jagged edges catch on one another. The rock locks into place. But the mantle below does not stop moving. The great conveyor belt of the deep earth keeps pulling. For decades, or even centuries, the plates remain perfectly stuck, silently building up an immense amount of tension, like a heavy rubber band being stretched tighter and tighter in the dark. This quiet accumulation of stress happens deep beneath the ground, completely unfelt by those of us resting on the surface. But eventually, the sheer pulling force of the earth overcomes the friction holding the rocks together. The jagged edges finally snap and slip past one another, lurching forward in a matter of seconds to catch up with the movement they missed over the past 100 years. We feel this sudden, natural release of tension on the surface as an earthquake. While they can sometimes feel surprising to us, an earthquake is simply the earth settling itself, exhaling a deep breath of built-up stress and continuing its slow, endless journey. Once the slip occurs, The plates lock together once again, the tension begins to slowly rebuild, and the peaceful stillness returns for another century. Finally, there are places where plates do not pull apart and do not slide past one another. There are places where they meet head-on. This is the third interaction, a majestic, slow-motion collision. When two tectonic plates converge, a fascinating dynamic of weight and density takes over, dictating exactly how the land will change. Let's imagine that one of these colliding plates is a heavy, dense oceanic plate made of dark, thin basalt, and it is crashing into a lighter, thicker continental plate. Because the oceanic rock is so much denser, it acts like a heavy anchor. As the two immense slabs of stone press together, the heavy oceanic plate yields. It gently bows downward and begins to slide entirely underneath the lighter continent. It sinks down into the dark abyss, plunging back into the hot, flexible mantle from which it was born millions of years ago. This sinking motion is called subduction, and it creates the deepest, most unfathomable trenches on our planet, plunging miles down into the ocean floor where no sunlight can ever reach. But the sinking rock does not go quietly into the deep. As it is pushed down into the blazing heat of the mantle, it brings with it cold water from the ocean and minerals from the surface. This unique mixture lowers the melting point of the surrounding mantle rock. Deep below the continent, pools of hot, liquid magma begin to form. Because this new magma is suddenly lighter than the solid rock around it, it begins to slowly burn and melt its way upward, rising like a hot air balloon through the continental crust until it finally erupts on the surface as a towering volcano. This is how the beautiful, snow-capped volcanic mountains of the Pacific Northwest and the Andes were born, a direct, fiery consequence of heavy ocean rock gracefully sinking into the depths. But what happens if the two colliding plates are both made of thick, lightweight continental crust? What if they are equally buoyant, like two massive blocks of wood meeting in the open sea? In this case, neither plate is heavy enough to sink into the mantle. When they meet head-on, with the unstoppable force of the earth pushing them together from behind, they have nowhere to go but up. Imagine two cars gently bumping bumpers, but the impact is perfectly slowed down over a period of 50 million years. The solid rock of the continents compresses, folds, and crumples, pushing massive sheets of stone high into the sky. This incredible, slow-motion buckling is exactly how the Himalayas were forged. India, floating on its own plate, slowly drifted across the ancient sea and collided squarely with the belly of Asia. The land crumpled, pushing the seafloor up into the clouds. This is why, if you were to climb to the very snowy summit of Mount Everest today, you would find the fossilized remains of ancient seashells resting quietly at the highest point on Earth, a quiet testament to a vanished ocean. All this vast, unimaginable architecture, the deep ocean trenches, the sprawling inland volcanoes, the towering mountain ranges, is built entirely on the slow, patient movement of whole continents interacting at their edges. It is a grand, beautiful machine, constantly destroying and remaking the surface of our world as you sleep. But to truly appreciate the stone that makes up these towering peaks and deep valleys, we must gently change our perspective. If we zoom in much closer, past the scale of continents, past the scale of mountains, and imagine holding a single piece of this ancient rock in the palm of our hand, we must ask, what is it actually made of? Let's step softly away from the grand, sweeping scale for a moment and look at the quiet, perfect building blocks of the Earth. Let's step softly away from the grand, sweeping scale for a moment. We have spent our time watching whole continents tear apart in slow motion and massive mountain ranges fold gracefully into the sky. It is wonderfully easy to get lost in the sheer, unimaginable immensity of the Earth. But the grandest architecture in the world is always built from the smallest, most quiet components. So, I want you to imagine bringing your focus all the way in. Picture yourself standing beside a cool, shallow river in a quiet forest. You reach down into the clear water and pick up a single, smooth stone. As it rests heavily in the palm of your hand, I want us to ask a beautifully simple question. What exactly are you holding? When you look closely at that stone, you might notice that it is not just one uniform, flat color. You might see tiny flecks of dark black, a faint shimmer of silver catching the light, or a dull, milky white resting in the background. A rock is not a single pure thing. It is a composite, a mixture, a gathering of different pieces. To understand the stone, we must understand the pieces it is made of. We call these individual, fundamental pieces minerals. They are the quiet, perfect building blocks of the entire planet. Every mountain, every grain of sand on every beach, and the deep, solid rock of the ocean floor is simply a vast collection of these tiny, beautifully structured minerals. To truly appreciate what a mineral is, it helps to think of the earth as an incredibly patient baker, and the rocks as the finished loaves of bread or complex cakes that emerge from the oven. When you bake, the final product is a mixture of many different things. But before you mix the batter, you have your pure, raw ingredients resting neatly on the counter: the pure flour, the granulated sugar, the fine salt. Minerals are the pure ingredients of the earth. You cannot break a mineral down into a simpler geological substance. A piece of pure quartz is quartz all the way through, down to the very last atom. But simply being a pure ingredient is not quite enough to earn the title of a mineral. The true magic of geology, and the reason rocks have such incredible strength and character, lies entirely in how those ingredients are organized. For a substance to be a true mineral, the atoms inside it must arrange themselves in a highly specific, perfectly orderly internal structure. They cannot be scattered about randomly, like a handful of loose change tossed onto a table. Instead, they must lock together in a repeating, geometric pattern. Imagine the frame of a well-built house, or the complex, interlocking steel scaffolding of a skyscraper. In architecture, strength comes from perfect geometry. The beams are spaced at exact intervals, joined at precise angles, repeating over and over again to create a structure capable of holding immense weight. Deep in the dark, microscopic world of the stone, atoms do exactly the same thing. They reach out and bond with one another in perfectly symmetrical, repeating frameworks. Depending on which specific atoms are present in the deep earth, perhaps oxygen, silicon, iron, or magnesium, they will lock together in different geometric shapes. Some form perfect tiny cubes. Others form delicate, sweeping hexagonal pyramids or long, needle-like prisms. This perfect internal architecture is what we call a crystal lattice. It is a stunning realization to know that the smooth, seemingly solid stone you imagined holding in your hand is actually composed of trillions of these microscopic, perfectly ordered geometric crystals, all locking arms in the dark. And this internal arrangement is not just a hidden detail. It completely dictates how the mineral behaves in the physical world. In fact, the structure is often more important than the ingredient itself. Let's explore a beautiful, everyday example of how this architecture dictates reality. Think of a simple lead pencil resting on a desk, and a brilliant diamond set in a ring. To our eyes, they could not be more completely different. The dark grey material inside the pencil, which is a mineral called graphite, is so incredibly soft that simply dragging it lightly across a piece of paper causes it to flake apart and leave a mark. It feels greasy to the touch and crumbles under the slightest pressure. A diamond, on the other hand, is the hardest naturally occurring substance on the planet. It is so unyielding that it can effortlessly scratch solid steel, and it catches and bends light with a brilliant, clear fire. Yet, despite these absolute extremes, graphite and diamond are made of the exact same ingredient. They are both made of completely pure carbon. There is absolutely no difference in what they are made of. The only difference in the entire world is how their atoms are arranged. In the soft graphite of the pencil, The carbon atoms are arranged in flat, two-dimensional sheets, like reams of loose paper stacked on top of one another. The bonds within each sheet are strong, but the bonds holding the separate sheets together are incredibly weak. So, when you apply the gentle pressure of writing, the sheets simply slide off one another, leaving a trail of carbon on the page. But in a diamond, the carbon was subjected to the crushing, agonizing pressure of the deep mantle we explored earlier. Under that immense weight, the carbon atoms were forced to abandon their flat sheets and lock together in a tightly woven, three-dimensional grid. Every single atom is strongly bound to four others, creating an interlocking, unyielding truss in every direction. There are no weak points, there is no room to slide. The pure strength of a diamond is simply the strength of perfect, unbreakable architecture. When you realize this, you begin to look at the world around you differently. The strength of the ground beneath your feet is not just a matter of heavy ingredients. It is a matter of profound, silent organization. But a single mineral, growing alone in the dark, does not make a mountain. To build the solid crust of the earth, these different minerals must come together. Imagine a space deep underground, filled with a mixture of different chemical ingredients. As the conditions become just right, microscopic crystals begin to form and grow. A crystal of pure quartz begins to build its framework here. A dark crystal of iron-rich mica begins to grow right beside it. As they slowly expand, building their perfect internal scaffolding atom by atom, they eventually run out of room. They bump into one another. But instead of stopping, they simply continue to grow into every available microscopic space, wrapping around one another, their edges locking together like the most complex, three-dimensional puzzle ever conceived. When millions of these different mineral crystals interlock and bind together into a single solid mass, they finally cross a threshold. They cease to be just a collection of pure ingredients, and they become a rock. The texture, the color, and the weight of that rock will depend entirely on which minerals grew together and how much time they had to build their structures before they were locked into place. And the very first of these rocks, the foundational stones upon which all the continents are built, are born in a place of unimaginable, glowing heat. Having looked closely at the quiet, perfect ingredients of the earth, we are now perfectly positioned to step back slightly and see how these beautiful structures are forged, which brings us gently into the fiery origins of stone. Let's pick up exactly where we just left off, carrying the memory of those microscopic, perfectly ordered mineral crystals in our minds. We now know that these crystals are the fundamental ingredients of the earth, the pure building blocks of all geology. But these ingredients do not simply assemble themselves in the cold dark. To fuse together into the massive, solid bedrock of our continents and our ocean floors, they must pass through a crucible. Every single piece of stone on this planet, no matter how cold or quiet it seems today, was once a glowing, molten liquid. The very first rocks, the foundational stones of the earth, are born entirely of heat, and we call them igneous rocks. The word igneous is a beautiful ancient term that quite simply means born of fire. To understand how this fiery birth happens, we must drift back down, just for a moment, beneath the brittle crust, into the crushing depths we explored earlier. Deep in the lower crust and the upper mantle, the conditions can sometimes shift. Perhaps a heavy, sinking tectonic plate introduces deep water into the hot stone, or perhaps a massive drop in pressure allows the stifling heat to suddenly take over. When this happens, the solid rock begins to melt. It transforms into a thick, glowing, heavy fluid that we call magma. I want you to imagine a reservoir of magma miles beneath the surface. It is not a chaotic, violently boiling cauldron, but rather a slow, heavy, deeply glowing fluid, confined in absolute darkness and immense pressure. Because this liquid rock is slightly less dense than the solid stone surrounding it, it naturally wants to rise. it behaves very much like a warm air balloon gently pushing its way up into the sky. The magma slowly burns, melts, and forces its way upward through tiny cracks and fissures in the crust, seeking a path to the surface. From here, the life of this liquid stone can take one of two profoundly different paths, and the path it takes will dictate exactly what kind of rock it will become. The deciding factor is beautifully simple. It is all a matter of time and temperature. Let us imagine the first path, the dramatic journey to the surface. Sometimes, the magma finds a clear, open fracture all the way up through the crust. It pushes upward, higher and higher, until it finally erupts out into the open air or pours out across the freezing ocean floor. The moment this liquid rock breaches the surface of the Earth, it undergoes a simple change in name. Magma becomes lava. Now, think about what happens to this glowing, thousands of degrees lava when it suddenly meets the cold night air or the freezing, crushing depths of seawater. The shock is absolute. The heat is instantly drawn out of the liquid stone. In geology, this is called rapid cooling, but rapid hardly does justice to the violence of the temperature drop. The lava freezes almost immediately into solid rock. We call rocks formed in this way extrusive igneous rocks, because they are extruded or pushed out onto the surface. Because the cooling happens so incredibly fast, something fascinating happens at the microscopic level. Remember the beautiful, orderly, repeating crystal structures of the minerals we built just a little while ago? Creating those intricate architectures takes time. The atoms need time to move around in the liquid, find their matching partners, and lock into their perfect geometric grids. But when lava is plunged into the cold ocean, the atoms are given absolutely no time at all. Imagine boiling sugar syrup in a warm kitchen. If you pour that boiling syrup slowly into a mold and let it sit for days, the sugar molecules will patiently build large, beautiful crystals, forming rock candy. But if you take that boiling pan of sugar and plunge it instantly into a bath of ice water, the syrup seizes. It freezes instantly into a smooth, solid sheet of hard glass. The molecules didn't have a single moment to arrange themselves. They were simply frozen exactly where they stood. This is exactly what happens to the cooling lava. The atoms scramble, panic, and freeze in place before they can organize. If the cooling is truly instantaneous, the result is a beautiful, dark, completely smooth volcanic glass called obsidian. If you run your thumb across a piece of obsidian, it feels perfectly slick and frictionless, like a dark mirror. If the lava cools just a little bit slower, taking perhaps a few days or weeks to solidify, it forms a heavy, dark, dense rock called basalt. The crystals in basalt are so microscopic that you could never see them with the naked eye. The rock looks uniformly dark and matte. This heavy, quickly cooled basalt is exactly what makes up the entirety of the deep ocean floor, wrapping around the globe like a dense, dark blanket. But what about the second path? What happens if the rising magma never quite makes it to the surface? Imagine a massive reservoir of liquid rock pushing upward, but miles below the ground, it hits an impenetrable ceiling of solid, unbroken crust. The magma becomes trapped. It pools in a massive subterranean chamber, surrounded on all sides by thick, insulating layers of stone. This liquid rock cannot cool instantly. It is wrapped in a geological thermos, trapped in the deep heat of the earth. Instead of freezing in seconds or days, this trapped magma will take hundreds of thousands, or even millions of years, to fully cool and solidify. We call these deeply formed stones intrusive igneous rocks, because they intrude into the deep spaces of the crust. Because this cooling process is so unimaginably slow, the atoms within the liquid have all the time in the world. They engage in a slow, elegant, microscopic dance in the dark. The silicon and oxygen atoms drift together, patiently building the beautiful clear pyramids of pure quartz. The iron and magnesium atoms gently seek each other out, building the dark, flaky sheets of mica. Century after century, millennium after millennium, these minerals slowly grow, expanding their perfect crystal lattices until they finally bump into one another and lock together. Because they had millions of years to grow, the individual mineral crystals become incredibly large. You do not need a microscope to see them. You can easily see them with the naked eye. This slow, patient cooling in the dark is how granite is made. If you picture a piece of granite, perhaps in the smooth, polished countertop of a kitchen, or the rough, towering face of a mountain, you know exactly what it looks like. It is a beautiful, speckled mosaic. You can see the pale white feldspar, the sparkling clear glass of the quartz, and the dark, sharp flecks of the darker minerals. Every single one of those distinct, visible specks is a mineral that was given the gift of time, allowed to grow to its full, beautiful potential in the insulated dark of the earth. Granite is the great, strong anchor of our world. While the heavy, fine-grained basalt lines the ocean floors, the lighter, coarse, deeply speckled granite makes up the thick, buoyant core of all the continents. It is the solid, enduring foundation that holds up the forests, the plains, and the cities. It is a beautiful contrast to consider. The exact same molten material, born from the exact same deep heat, can become a smooth, black piece of volcanic glass or a rough, speckled, enduring block of granite, depending entirely on whether it was rushed by the cold surface or cradled patiently in the deep earth. But if intrusive rocks like granite are born miles beneath the ground, trapped under thick blankets of crust, you might wonder how we are able to see them at all. How do these deep, hidden stones end up forming the towering peaks of places like the Rocky Mountains or the Sierra Nevada? The answer lies in the slow, relentless movement of the tectonic plates we explored earlier. The buckling and folding of the crust pushes these deep stones upward, lifting the ancient, hidden magma chambers high into the sky. And yet, simply pushing them upward is not enough. To reveal the granite, the thick layers of rock that originally trapped it must be cleared away. The moment the earth pushes these deep stones up into the sky, exposing them to the open air, a new, incredibly gentle, yet unstoppably powerful process begins. The rock is handed over from the fiery heat of the deep to the cold, persistent touch of the sky, leading us seamlessly toward the patient sculptors of the surface and the soft, silent accumulation of time. Let's follow that new, gentle process as the earth hands the stone over to the sky. We have just witnessed the dramatic birth of granite, forged in the deep, silent heat of the crust, and finally pushed upward into the open air to form the towering peaks of our continents. But this is not the end of the stone's journey. In fact, the moment a rock is exposed to the surface, an entirely new chapter begins. The Earth is a restless creator, but it is also a relentless dismantler. Nothing on the surface of our planet, no matter how hard or heavy it is, lasts forever. As soon as a mountain is pushed up into the sky, the atmosphere goes to work, beginning the long, patient task of taking it back down. This slow dismantling is the foundation of the second great family of rocks on our planet, sedimentary rocks. They are not born of fire, but of patience, water, and time. To understand how these rocks are formed, we must first look at the invisible forces acting on the landscape every single day. The process begins with something called weathering. Think about a magnificent solid granite cliff face, baking under the hot midday sun and then freezing under the cold starry night. This constant, daily fluctuation in temperature causes the surface of the rock to expand very slightly during the day and contract at night. It is a tiny, microscopic movement, but over centuries and millennia, this endless expanding and contracting causes the hard minerals to crack and loosen. Now, imagine the rain. When water falls from the sky, it is not perfectly pure. It picks up a tiny bit of carbon dioxide from the air, making it very slightly acidic. When this gentle, Acidic rain falls on the granite cliff. It doesn't wash the rock away instantly, but it reacts chemically with the weaker minerals inside the stone. The feldspar, one of the main ingredients of granite, slowly dissolves and turns into soft clay. The beautiful, sparkling quartz crystals, which are much harder and resistant to the acid, are suddenly left unsupported. They loosen and they fall away. This process is entirely invisible in the moment. If you were to sit and watch a mountain for a year, it would look perfectly unchanged. But think of the deep time we explored earlier. Imagine running a piece of fine sandpaper, very lightly, over a piece of hardwood for 100,000 years. The persistent touch of rain, the gentle wedge of freezing ice expanding in tiny cracks, and the constant scouring of the wind slowly break the massive, towering mountain down into tiny fragments. The rock is reduced to rough pebbles, fine grains of pale quartz sand, and microscopic particles of smooth clay. We call all these broken pieces sediment. Once the mountain is broken down, gravity takes over. Gravity is the tireless engine of the surface, always pulling everything downward toward the lowest point. The rain washes the loose sand and clay into small streams, and those streams gather together to form powerful, rushing rivers. The rivers act as massive, natural conveyor belts, carrying millions of tons of this sediment away from the high mountains and transporting it gently downward, mile after mile, toward the valleys, the quiet lakes, and finally, the vast open ocean. When the fast-moving river finally reaches the ocean, the water slows down. It loses its energy, and because the water is no longer rushing forward, it can no longer carry the heavy particles of sediment it brought from the mountains. The river drops its load. Imagine standing on a quiet beach, watching the waves roll in. Beneath the surface of the water, a silent, continuous snowstorm of sand and mud is settling to the sea floor. Year after year, century after century, layer upon layer of this sediment piles up. Think of a stack of papers accumulating on a desk, one softly landing on top of the other, day in and day out. The sheer volume of material is staggering. Over millions of years, these layers of sand and mud can grow to be thousands of feet thick, stretching endlessly across the dark, flat plains of the ocean bottom. As these layers pile higher and higher, the environment at the bottom begins to change. The sand and mud resting at the very bottom of the pile are subjected to an immense, crushing weight from all the water and the millions of tons of new sediment resting above them. This deep, heavy pressure begins to squeeze the loose grains of sand tightly together, forcing the water out from the microscopic spaces between them. But pressure alone is not enough to turn loose sand into solid stone. The sediment needs a binder. Fortunately, the ocean water that was squeezed out is not empty. It is rich with dissolved minerals, like silica and calcium, which were also washed down from the mountains. As the water is forced out of the tightly packed sand, it leaves these dissolved minerals behind. The minerals crystallize in the tiny microscopic spaces between the grains of sand, acting like a perfect, natural cement. They glue the loose pieces together, binding them into a solid, heavy mass. This is lithification, the beautiful, silent moment when soft mud and loose sand finally become a rock. The transformation is complete. We now have sedimentary rocks. Because these rocks are made from the broken pieces of older rocks, they possess a completely different character than the solid, crystalline granite we explored before. Sedimentary rocks are the memory keepers of the earth. If you look at a piece of sandstone, you can clearly see the individual, rounded grains of quartz sand, glued perfectly together. You are looking at a fossilized beach or an ancient desert dune, perfectly preserved in stone. If you look at a piece of shale, which is made from tightly compressed layers of fine clay, you are looking at the fossilized mud of a quiet, ancient lakebed. And because they are laid down layer by layer over vast stretches of time, Sedimentary rocks form the magnificent striped canyons we see in places like the American Southwest. When you stand on the rim of the Grand Canyon and look down at the dizzying bands of red, white, and tan stone, you are not just looking at a beautiful landscape, you are looking at a physical timeline. Every single colored stripe represents a different environment, a different era in the Earth's history, stacked neatly on top of one another. The sandstones tell of ancient, wind-swept deserts. The limestones tell of warm, shallow seas teeming with life. The dark shales tell of deep, muddy swamps. Sedimentary rocks are the only rocks that can truly record the passage of time on the surface. They hold the shapes of ancient ripples left by a gentle current millions of years ago, perfectly frozen in the stone. They hold the fragile, intricate fossils of plants and animals that lived and died in those vanished environments. They are the great, silent archives of the planet. But the Earth, as we know, is never finished. Even these massive, solid layers of memory are not safe from the slow, relentless movement of the planet. As the tectonic plates continue their endless drift, these thick, heavy layers of sedimentary rock can be dragged deeper into the crust, or caught in the slow, agonizing collision of continents. The gentle pressure that formed them is about to be replaced by something far more intense. We are drifting deeper again, away from the quiet surface and back into the dark, where the temperature and the pressure begin to rise, preparing to transform the stone one final time. We are drifting deeper again, away from the quiet, sunlit surface and back down into the absolute dark. We just watched the gentle, patient accumulation of sand and mud settling at the bottom of an ancient sea, slowly turning into sedimentary rock. But the Earth is a restless, dynamic system, and it rarely leaves its creations alone for long. As the millions of years pass, those thick, heavy layers of sedimentary rock, or even the solid, crystalline igneous rocks we explored earlier, can become buried. They might be covered by thousands of feet of new sediment piling up above them, or they might be caught in the slow, agonizing collision of two massive tectonic plates. Either way, the rock is pushed downward, descending miles into the crust of the Earth. As the stone sinks deeper, the comforting chill of the surface is left far behind. The environment begins to change drastically. The rock is subjected to two overwhelming forces: the immense crushing weight of the world pressing down from above, and the intense rising heat radiating from the glowing mantle below. We have returned to the deep forge of the Earth, but the transformation that happens here is entirely different from the fiery birth of magma we witnessed earlier. The most crucial rule of this deep environment, the defining characteristic of what we call a metamorphic rock, is that the stone must never melt. If the rock gets too hot and crosses the threshold into a liquid, it becomes magma, and its history is completely erased. It will eventually cool and become an igneous rock all over again. Metamorphosis is the art of changing right on the very edge of destruction. The rock remains completely solid throughout the entire process, yet it is completely, fundamentally transformed. To understand how a solid thing can change its entire identity without ever melting, we can look at a familiar experience from the kitchen. Imagine taking a soft, airy piece of fresh white bread. If you place that bread into a heavy, cast-iron sandwich press and push down firmly while applying heat, the bread doesn't melt into a liquid. The ingredients remain exactly the same, but the heat and the intense pressure completely alter the texture, the density, and the structure of the food. It goes from being soft and airy to dense, hard, and crisp. Deep inside the Earth, a similar, though far more profound, process occurs. When a solid rock is heated to hundreds of degrees, the atoms inside the minerals become incredibly energized. They begin to vibrate intensely. Even though they are trapped in a solid state, the heat gives them just enough energy to break their old chemical bonds and slowly, patiently move around. They rearrange themselves. The microscopic crystals within the rock begin to dissolve into their neighboring crystals, merging together and growing into entirely new, beautiful forms. We can see this beautiful, silent alchemy most clearly when we look at limestone. As we discovered earlier, limestone is a sedimentary rock made almost entirely from the crushed, muddy remains of ancient seashells resting at the bottom of the ocean. It is usually dull, grey, and somewhat chalky. But if a thick layer of limestone is dragged deep into the earth and heated for 1,000,000 years, the microscopic fragments of calcium carbonate begin to change. They slowly unbind and rebind, merging into larger and larger crystals. The tiny grey fragments of shell are completely erased. The stone is purified. When this rock is eventually pushed back to the surface, it is no longer a dull limestone. It has been transformed into a brilliant, swirling, luminous rock called marble. The pure, interlocking crystals of marble catch the light and hold a deep, smooth polish, which is exactly why sculptors and architects have sought it out for centuries. The ingredients have not changed at all. It is still just calcium and oxygen, but the deep heat has given the stone a completely new, elegant architecture. But heat is only half of the metamorphic story. The other profound architect of change is pressure. When tectonic plates slowly collide, they don't just push the rock downward, they squeeze it from the sides with unimaginable horizontal force. The stone is caught in a slow-motion vice. Imagine taking a handful of flat, silver coins and dropping them into a glass jar. They will land in a completely random, disorganized jumble, facing in all different directions. Now, imagine you could somehow squeeze the sides of that glass jar inward. As the space shrinks, the coins would be forced to shift. Eventually, to survive the pressure, every single coin would lay perfectly flat, stacking neatly against one another, perpendicular to the direction you are squeezing. The minerals inside a rock do exactly the same thing. When a rock is squeezed by the collision of continents, the heat allows the minerals to grow, but the pressure forces them to grow in a very specific direction. The minerals flatten out, aligning themselves in beautiful, parallel layers. Geologists call this process foliation. We can watch this progression beautifully by following a single, humble rock as it descends into the deep. Let's start with a piece of shale, which is a soft, sedimentary rock made of dried mud. If you gently squeeze and heat that shale, the microscopic clay minerals flatten and align. The dull mud transforms into slate, a very hard, smooth rock that splits perfectly into perfectly flat, thin sheets, like pages in a heavy book. If the earth continues to pull that slate deeper, the heat and pressure rise. The atoms are forced to abandon their old structures entirely. They begin to build brand new minerals that didn't even exist in the original mud. Deep red, geometric garnets begin to form in the solid rock. The flat layers become coated in shimmering, silvery sheets of a mineral called mica. The rock has now become a schist, sparkling and glittering in the dark. And if we push it even further, right to the absolute brink, just a few degrees shy of melting entirely, the rock undergoes one final, desperate reorganization. To survive the agonizing pressure, the light-colored minerals and the dark-colored minerals separate from one another. They gather into distinct, alternating bands, creating a stunning, deeply striped rock called gneiss. When you look at a piece of gneiss, with its beautiful, wavy ribbons of black and white stone, you are looking at a rock that survived the absolute extremes of our planet. You are looking at a stone that was pushed to the very edge of existence, but refused to melt. Metamorphic rocks are the great survivors of geology. They hold within their flattened layers and their enlarged crystals the memory of deep time and immense forces. They tell us about ancient continental crashes, about deeply buried oceans, and about the slow, heavy breathing of the Earth's crust. They are the final, beautiful expression of the stone before it returns to the fire. And this realization brings a quiet sense of completion to our journey. We have seen rock born from the glowing magma, We have seen it worn away by the gentle rain and the wind, settling into the soft, layered memories of sedimentary stone. And now we have seen it dragged back into the deep, squeezed and heated until it transforms into something entirely new. We have witnessed every stage of the stone's long life, but the earth wastes nothing, and it leaves nothing unfinished. Let's set that idea down now, fully formed, and let our attention drift naturally toward the grand design of it all, connecting these isolated moments into the perfect, continuous recycling system that keeps our world alive. Let's set that idea down now, fully formed, and let our attention drift toward the grand design of it all. Over our time together, we have looked at the different stones of the earth as if they were isolated chapters in a book. We watched the fiery birth of igneous rock, forged in the deep, glowing magma chambers and cooling in the dark. We sat with the slow, patient accumulation of sand and mud, watching it compress over millions of years into heavy sheets of sedimentary rock. And most recently, we descended into the crushing depths to witness the great metamorphosis, where heat and pressure bend and align solid stone into beautiful, swirling new forms. It is wonderfully easy to look at a polished piece of marble or a rough chunk of granite and view it as a finished product, a permanent, static object that has reached its final form. But if we recall the vast, stretching ocean of deep time that we stepped into at the very beginning of our journey, we can start to see a much larger, more beautiful picture. Think about how we operate in our modern, everyday lives. We build our world on a straight line. We extract raw materials from the ground, we manufacture a product, we use it for a handful of years, and eventually we discard it. It is a journey from creation to waste. But the Earth operates on an entirely different, infinitely more elegant principle. The Earth wastes absolutely nothing. There is no hidden landfill of used mountains, no discarded pile of ancient stone resting in the deep ocean. Our planet is a perfect, closed system. Every single grain of sand, every jagged peak, and every glowing drop of lava is part of a continuous, majestic recycling system that geologists quietly refer to as the rock cycle. Picture a great wheel turning effortlessly and silently in the dark expanse of space. It is a wheel that has been spinning for over 4 billion years, driven by the intense heat of the core below and the slow pulling of gravity above. On this wheel, there is no true beginning, and there is no final end. There is only a slow, graceful transformation from one state of being to another. To understand the profound beauty of this cycle, let us follow a single, microscopic particle of stone, perhaps a tiny, clear crystal of quartz, as it takes a grand, unimaginably long ride on this turning wheel. Let us imagine this quartz crystal is born in fire, cooling patiently deep within a massive chamber of granite, safe beneath the sprawling weight of a continent. It is an intrusive, igneous rock, solid and completely unyielding. For tens of millions of years, it rests in the absolute dark, perfectly still. But eventually, the slow, relentless movement of the tectonic plates pushes this deep rock upward. The land above it is stripped away by wind and water, and our tiny quartz crystal is suddenly, quietly exposed to the open sky. Now, the slow dismantling begins. The freezing ice of winter expands in the microscopic cracks of the stone, and the gentle, persistent rains of spring wash over it. Over 1 million years, the solid granite is broken down. Our tiny crystal is loosened and washed away into a rushing mountain stream. It tumbles over smooth river stones, traveling hundreds of miles, rounding its edges until it finally reaches the quiet, vast ocean. It sinks to the bottom, coming to rest in the cold, silent dark of the seafloor. Here, it is buried by millions of tons of other sand, silt, and mud, falling like a slow-motion snowstorm from the water above. The crushing weight of the ocean and the earth presses down on it, and minerals in the water slowly cement it into place. Our crystal has been reborn. It is no longer a piece of a fiery granite mountain. It is now a single grain of sand locked inside a heavy, solid sheet of sedimentary sandstone. It has changed from a rock born of heat to a rock born of gravity and water. But the great wheel continues to turn. The ocean floor is not a permanent resting place. The tectonic plate carrying our sandstone is slowly, relentlessly dragged toward the edge of a massive continent. Over millions of years, the heavy rock is pulled downward, plunging deep into the Earth's crust through the process of subduction. The freezing chill of the ocean is left far behind, replaced by the suffocating, rising heat of the mantle. The pressure from the crashing continents squeezes the rock with unimaginable force. Our tiny quartz crystal, still trapped in the solid stone, is heated until it almost softens. It merges with the surrounding grains, flattening and stretching to survive the crushing weight. The dull, sandy rock has metamorphosed into a stunning, striped gneiss. It is a survivor of the deep, fundamentally changed by pressure without ever melting. And yet, even this is not the end. The heavy stone is dragged deeper still, until the heat finally becomes too absolute to resist. The rock is pushed over the invisible threshold. It melts. The solid, crystalline architecture completely dissolves, and the stone returns to a glowing, fluid pool of heavy magma. It waits in the dark, gathering heat, preparing to rise to the surface and cool into a brand new igneous rock, starting the journey all over again. It is a beautiful, complete circle. But perhaps the most incredible part of this great wheel is that a rock does not have to travel the entire path in perfect order. The Earth is far more creative and complex than a simple loop. The cycle is an endless web of possibilities, and any rock can become any other type of rock, given the right set of circumstances. A towering mountain of igneous granite can be pushed down by colliding tectonic plates and squeezed directly into a metamorphic rock without ever seeing the sky or being broken down into sand. A thick layer of sedimentary sandstone resting at the bottom of the ocean can be lifted up by a shifting fault line, exposed to the rain, and weathered right back into loose sand, becoming a completely new sedimentary rock without ever descending into the hot mantle. Even a metamorphic rock, hardened deep in the crust, can be lifted to the surface and gently washed away to the sea. The wheel has many spokes, and the stone can travel any path, moving always at the creeping, peaceful pace of deep time. There is a deep, abiding comfort in this realization. When you look out at the landscape tomorrow, you will see a world in transition. The mountains you see on the horizon, the valleys you drive through, the smooth stones you skip across a quiet lake, they are not permanent fixtures. They are just temporary resting places for material that has been traveling since the world was young. The Earth is constantly renewing itself, quietly erasing the old to build the new, ensuring that the planet never truly grows rigid or dead. Every grain of soil holding a forest, every towering cliff face, is simply pausing in its long, beautiful journey. And yet, even as this great wheel turns, constantly recycling the crust of our world, it does not erase everything perfectly. As these thick layers of rock are laid down, buried, and lifted back up over millions of years, they manage to leave behind a quiet, enduring record. They capture fleeting moments in time, stacking them up in the dark like pages in a massive, ancient book. And this realization leads us softly forward, away from the sweeping movement of the cycle, to ask how we might look at these stacked layers, and how we might learn to read those deep, rocky pages. A moment ago, we ended with the idea of stacked layers of stone, resting quietly in the dark. Let us pick up that thread right where we left it. If the rock cycle is the endless turning wheel of the Earth's engine, then the layers of sedimentary rock left behind are the planet's memory. When you look at the sheer vertical face of a deep canyon, or even a steep highway cut where engineers have blasted through a hill, you are not just looking at a wall of dirt and stone. You are looking at the pages of a massive, ancient, beautifully preserved book. the careful, patient study of these rocky pages is a branch of geology known as stratigraphy. And the most wonderful thing about stratigraphy is that you do not need a laboratory or complex machinery to understand it. You only need the quiet, everyday logic you already use to navigate your life. The fundamental rule of reading these deep layers is wonderfully simple, grounded entirely in common sense. It is called the law of superposition. To picture this, think about a spot in your home where things tend to accumulate, perhaps a laundry basket, a pile of mail on a desk, or a stack of magazines on a coffee table. If you look at that stack of mail, you know instinctively how it was formed. The envelopes resting at the very bottom were placed there weeks ago. The letters in the middle arrived last week, and the envelope resting lightly on the very top was tossed there just this afternoon. Unless someone came into the room and deliberately flipped the entire stack upside down, the oldest things are always at the bottom, and the newest things are always at the top. The earth works in exactly the same way. When gentle rivers carry mud and sand into a quiet lake, or when millions of tiny shells drift down to the bottom of a calm ocean, they settle flat on the ground. And that first, bottommost layer is laid down. A million years later, the climate shifts, and a new layer of sand washes in, gently settling directly on top of the old mud. As long as these layers remain relatively undisturbed, every single layer of rock is always younger than the one it rests upon, and older than the one resting on top of it. By reading these layers from the bottom to the top, your eyes are physically traveling forward through time. But the Earth, as we have learned, does not always leave its creations undisturbed. The tectonic plates wander and continents collide in slow, heavy impacts. This introduces a second beautiful piece of logic to our reading. When sediment settles in a body of water, gravity dictates that it must spread out in perfectly flat, horizontal sheets. Think of pouring a thin pancake batter onto a hot griddle. It naturally flows outward until it is perfectly flat and level. It does not form steep, jagged peaks. The Earth's layers are poured in the same way. Geologists call this original horizontality. So, what does it mean if you are driving past a mountain and you see distinct, striped layers of sedimentary rock that are not flat, but are tilted steeply at a 45-degree angle? Or worse, what if you see layers that are folded and crumpled back and forth, like an accordion? Applying our quiet logic, we know the layers could not possibly have formed that way. Gravity would not allow mud to settle on a steep incline without sliding down. Therefore, the layers must have been laid down perfectly flat over millions of years, and then, sometime after they turned to solid stone, a massive tectonic force pushed them and tilted them into the sky. Simply by noticing the tilt, you have uncovered a sequence of events. First, the quiet settling of the sand, then the agonizing squeeze of the continents. We can take this logic one step further to solve even more complex puzzles in the stone. Imagine that you bake a beautiful, multi-layered cake. You let it cool completely on the counter. Then, you take a sharp knife and slice cleanly right down through the center of the cake. Which event happened first? The baking of the cake or the slicing of the knife? It is obvious to us that the cake had to exist in its entirety before it could be cut. This simple idea is known as the law of cross-cutting relationships. Sometimes, when looking at a cliff face, you will see flat, beautiful layers of sedimentary rock, but there is a jagged, dark line of igneous basalt slicing vertically right through all of them. That dark line is a magma intrusion, a place where liquid rock from the deep mantle forced its way up through a crack in the earth. Because of our simple rule, we know immediately that the horizontal layers are the oldest part of the story, and the magma that sliced through them is much younger. The rock must be there before it can be broken. Once we understand how to read the sequence of the pages, we can finally begin to read the story written upon them. The colors, textures, and thicknesses of the rock layers tell us exactly what the environment was like on that exact spot on the Earth. millions of years before humans ever existed. Imagine standing at the bottom of a deep gorge, looking at the lowest, oldest layer of rock. It is a thick, brilliant white band of limestone. From our earlier explorations, you know that limestone is made of crushed shells and coral. This tells you, with absolute certainty, that the dry, dusty canyon you are standing in was once the floor of a warm, sunlit, shallow, tropical sea. Now, move your eyes up to the next layer. Resting directly on top of the white limestone is a dark, flaky, organic band of black shale. Shale is formed from deep, oxygen-starved mud. The story of the Earth is unfolding right in front of you. Over millions of years, the ocean slowly retreated, and that warm, sunlit sea transformed into a stagnant, muddy, coastal swamp. Look up one more layer. Resting on top of the dark shale is a massive, towering cliff of brilliant red sandstone. The sand grains are beautifully rounded, and the deep red color comes from iron oxidizing or rusting in the open air. The story changes again. The dark swamp completely dried up. The rains stopped falling, and for millions of years, this land was a vast, wind-swept, blazing desert, covered in towering sand dunes that eventually fused into stone. You've just read 100 million years of climate change, ocean currents, and shifting ecosystems, all without leaving your spot, simply by looking at the color and texture of 3 layers of rock. It is a deeply grounding experience to realize that beneath our feet lies a perfect, enduring record of everything the world used to be. Before we rest here, however, let me whisper where we're headed next, not to rush, but to plant a seed. We can only read these magnificent, striped pages because they have been revealed to us. The vast majority of the Earth's sedimentary record is buried miles beneath the ground, hidden completely in the dark. In order for us to see a towering canyon wall, the millions of tons of earth resting above it must be painstakingly cleared away. The pages of the book must be sliced open. And so, we are naturally led to ask what incredible forces possess the strength to slice through solid continental rock. As we will gently explore next, the towering mountains and deep valleys we see are not just pushed up from below, they are carefully, tirelessly sculpted from above. A moment ago, we ended with the realization that the deep, beautiful layers of the Earth's memory, those stacked pages of ancient seabeds, deep swamps, and petrified deserts are largely hidden from our view. They are buried under millions of tons of solid rock, resting peacefully in the dark, and yet we know they exist. We can read their stories on the sheer, towering walls of massive canyons and deep valleys. But in order for us to see those deep pages, the heavy stone resting above them had to be carefully, painstakingly cleared away. And so, we are naturally led to ask, what incredible force possesses the strength to slice through solid continental rock, hundreds of miles wide and thousands of feet deep? The answer is beautifully poetic, and it reveals one of the greatest paradoxes of our planet. The towering, unbreakable mountains and the vast, unyielding plateaus are not brought down by heavier stone or violent explosions. They are patiently, slowly dismantled by the softest, most yielding substances on Earth, water and air. The great, untiring sculptors of the planet's surface are simply water and wind. Let us first consider water. In our daily lives, we experience liquid water as something completely yielding. When you run your hand through a bath or dive into a swimming pool, the water instantly parts around you. It holds no shape of its own. It seems entirely incapable of doing any real damage to something as hard as a granite mountain. But when you combine the fluid nature of water with the pulling force of gravity and the vast, stretching expanse of deep time, water becomes the most powerful, unstoppable tool on the planet. Imagine standing on a high, forested ridge during a gentle rainstorm. A single drop of rain falls from the sky and lands on a massive boulder. That single drop does absolutely nothing to the stone. But as millions of drops fall, they gather together. They form a tiny trickle, which merges with others to form a small stream wandering down the side of the mountain. As this water moves, it does something crucial. It picks up the tiny, microscopic fragments of rock and soil that have been loosened by the weather. This is the secret of water's great strength. The water itself is not slicing the rock. Rather, the water is carrying millions of tiny, sharp, abrasive tools. The grains of sand, the small pebbles, and the heavy, rolling cobbles caught in the current are dragged along the bottom of the riverbed. As they bounce and scrape against the solid stone beneath them, they act exactly like a piece of heavy sandpaper. Every single grain of sand that washes over a rock in a riverbed removes a microscopic, invisible layer of stone. Now, picture this process running continuously for 10 million years. You are standing on the rim of a massive, echoing canyon. The ground drops away beneath your feet, plunging a mile straight down into the earth, revealing a stunning, striped canvas of red, gold, and white rock. Way down at the very bottom, looking like a thin, winding ribbon of dark green, is the river. To your eyes, it looks entirely too small and too peaceful to have carved a gorge so impossibly vast. But it did. The carving of a canyon is a beautifully slow, dual process. While the river acts as a relentless, downward-cutting saw, the tectonic plates of the earth are doing their own quiet work. Over millions of years, the deep forces of the mantle slowly pushed that entire landscape upward into the sky. Imagine pushing a block of wood slowly upward into a spinning saw blade. The river stayed exactly where it was, bound by gravity, persistently scraping and cutting its way downward, while the land itself rose up around it. It is a perfect, agonizingly slow dance between the rising crust and the falling water, resulting in the breathtaking, open wounds we call canyons. But liquid water is not the only artist at work. If we travel away from the rushing rivers and step into the vast, quiet expanses of the world's great deserts, we find a landscape that is shaped by an entirely different, completely invisible sculptor. In places where rain rarely falls, the wind becomes the master of the stone. Wind, like water, is a fluid. We cannot see it, but it has mass, and it exerts force. When you stand on a beach on a windy day, you can feel the sting of the sand hitting your legs. The wind is picking up the finest, lightest grains of quartz and blowing them across the land. And just like the river, the wind uses these grains of sand as its tools. Imagine a towering, solid wall of red sandstone standing alone in a dry, silent desert. The wind blows across the open plains, carrying a sweeping cloud of fine, abrasive dust. As the wind hits the rock wall, it sandblasts the stone. But the wind is a very delicate, selective artist. A river cuts downward with blunt, heavy gravity, but the wind swirls, it eddies. It searches out the very slightest weaknesses in the rock. Perhaps, halfway up that massive sandstone wall, there is a patch of stone where the natural cement holding the sand grains together is just a little bit weaker. The wind finds it. Century after century, the wind blows against that softer patch, slowly loosening and carrying away grain after grain, creating a small, shallow depression in the cliff. Over thousands of years, that depression grows deeper and deeper, hollowed out by the invisible, swirling air. Eventually, the wind breaks completely through to the other side. The weak stone is gone, leaving only the stronger, harder rock standing perfectly intact above and around it. The result is a magnificent, sweeping natural arch of stone, framing the blue sky, looking as though it were carefully carved by human hands. The wind also carves tall, smooth pillars, balances massive, heavy boulders on impossibly narrow pedestals, and etches beautiful, sweeping grooves into the sides of cliffs. It is a slow, quiet artistry, completely devoid of the rushing noise of a river, accompanied only by the soft, endless sighing of the dry air. Together, the rivers of water and the sweeping currents of wind take the massive, jagged, heavy forms pushed up by the Earth's interior and soften them. They round the sharp edges, they carve the valleys, and they expose the deep, striped layers of memory hidden within the crust, allowing us to read the history of the world. They turn a chaotic planet of breaking rock into a landscape of breathtaking, sculpted beauty. And yet, while the flowing rivers and the swirling winds are the most constant sculptors of our world, there is one more tool that the Earth uses to shape its surface. It is a tool born of water, but it possesses a strength and a weight that a gentle river could never match. When the climate cools and liquid water is allowed to freeze and gather into massive, heavy sheets, it changes the landscape not with the delicate touch of a chisel or the soft sweep of sandpaper, but with the terrifying, unstoppable force of a slow-moving plough. Let's drift away from the warm deserts and the rushing streams, and let the air grow cold around us as we prepare to trace the slow, heavy path of frozen water. Let us drift away from the warm, sun-baked deserts and the rushing, energetic streams. I want you to let the air grow cold around us in your mind. We are leaving the lowlands behind and traveling far up into the high, silent altitudes of the great mountain ranges, or perhaps far to the north, near the quiet, solitary poles. Up here, the climate is fundamentally different. When winter arrives and the snow falls, covering the rugged peaks in a blanket of blinding white, it does not melt when the spring returns. The air simply remains too cold. The seasons change, the calendar turns, but the winter never truly releases its grip. And in this perpetual cold, a new, magnificent geological sculpture is born. To understand how a glacier forms, we have to look closely at a single, delicate snowflake. When snow first falls, it is incredibly light and airy, full of empty space and intricate, fragile arms. But when that snow survives the summer, and the next winter brings another heavy snowfall, the new snow rests entirely on top of the old. Year after year, decade after decade, layer upon layer of snow accumulates. Think of a massive, down-filled comforter. If you stack a dozen of them on top of one another, the fluffy feathers at the very bottom are pressed flat by the sheer weight resting above them. The snow behaves in the exact same way. The immense, compounding weight of the new snow presses down on the older layers beneath it. The delicate, airy structure of the snowflakes is crushed. The air is slowly, patiently squeezed out. Over many years, the snow transforms into coarse, granular ice, and eventually, under the continuing pressure, it fuses into a dense, completely solid block. Because almost all the air bubbles have been forced out, this deep ice does not look white. It takes on a beautiful, haunting, pale blue color. This massive, heavy expanse of solid blue ice is a glacier. But a glacier is not simply a frozen lake or a stationary block of ice. Because it is so unimaginably heavy, and because gravity is always pulling downward, this massive structure begins to move. It is, quite literally, a river of ice flowing down the side of the mountain. You might wonder how a completely solid block of hard ice can possibly flow like a river. The answer lies in the intense pressure trapped deep at the bottom of the glacier, recalling the behavior of the hot mantle we explored earlier. Deep inside the glacier, under the crushing weight of hundreds or even thousands of feet of ice, the frozen water actually becomes slightly flexible. It bends and stretches, creeping forward in a slow plastic flow. At the very same time, something equally fascinating happens right where the bottom of the glacier meets the solid rock of the mountain. The intense pressure actually lowers the melting point of the ice resting directly against the stone. This creates a microscopic, slippery layer of liquid water at the very base of the glacier. This thin film of water acts exactly like a lubricant, like a sheet of pure oil spread across a smooth floor. Cradled on this frictionless layer of meltwater, and pushed from behind by its own staggering weight, the entire glacier begins to slide downhill. The movement is incredibly slow. A fast-moving glacier might travel a foot or two in a single day. A slow one might only move a few inches in a year. If you were to sit beside it, you would see absolutely no motion. But make no mistake, this creeping, silent river of ice is one of the most powerful forces of destruction and creation on the planet. As we saw earlier, a river of liquid water acts like a downward cutting saw, using loose sand to carve a sharp, V-shaped groove into the rock. But a heavy glacier acts like a massive, unstoppable bulldozer. As the ice slides over the mountain, it doesn't just flow around obstacles, it consumes them. Imagine a fractured, uneven piece of bedrock jutting up from the ground. As the bottom of the glacier slides over this bump, meltwater seeps into the deep cracks in the stone. When that water refreezes, it expands, gripping the rock like a vice. Then, as the billions of tons of ice continue their slow, unstoppable march forward, the glacier simply tears the massive chunk of rock right out of the ground. This process is called plucking. The glacier incorporates these torn boulders into its own icy belly, carrying them along for the ride. Now, imagine the bottom of that glacier. It is no longer just smooth ice. It is studded with heavy, sharp, jagged boulders and millions of smaller stones, all held firmly in a matrix of frozen water. As this heavily armored underbelly grinds relentlessly against the solid mountain beneath it, it acts like the most aggressive, heavy-duty sandpaper imaginable. It gouges deep, straight scratches into the bedrock and grinds the surface stone down to a fine, powdery flour. Through this dual process of plucking and grinding, the glacier completely transforms the landscape. It does not carve a narrow, sharp valley like a river. Instead, it plows through, tearing away the sides of the mountains, smoothing the rough edges, and hollowing out a vast, wide, sweeping U-shaped valley. If you have ever seen a photograph of Yosemite Valley, with its massive, sheer, vertical granite walls and its perfectly flat, wide floor, you are looking at the unmistakable masterpiece of a vanished glacier. When a glacier finally reaches the edge of a continent and meets the sea, it carves these deep, U-shaped valleys right down into the ocean floor. When the ice eventually retreats, the seawater rushes in to fill the beautifully carved voids, creating the stunning, steep-walled coastal inlets we call fjords. But glaciers are not only defined by what they carve away, they are also defined by what they leave behind. Remember that a glacier operates like a massive conveyor belt, carrying millions of tons of torn rock, gravel, and sand down from the high peaks. Eventually, the ice reaches an altitude where the air is warm enough to melt the frozen water. The front edge of the glacier stops advancing. As the ice softly melts, it simply drops everything it was carrying. It leaves behind massive, curving ridges of piled-up earth and stone, marking the exact spot where the ice finally yielded to the warmth. And sometimes it leaves behind something truly strange, a massive, solitary boulder the size of a house, resting alone in the middle of a perfectly flat, grassy plain. Geologists call these erratic boulders. They are pieces of the high mountains, carried for hundreds of miles inside the belly of the ice, and gently set down on the soft earth when the frozen river finally melted away. They sit like abandoned luggage from a very long, very ancient trip. When the climate eventually warms and the great ice ages come to an end, these massive glaciers softly melt and recede back to the highest peaks. They leave behind a world that has been beautifully smoothed, deeply carved, and reshaped by the patient power of the cold. But as the miles of thick ice transform back into liquid water, all of that moisture must go somewhere. Some of it forms the beautiful, clear, high mountain lakes that dot the U-shaped valleys, and much of it flows away into the rushing rivers we explored before. But not all water stays on the surface. In fact, a vast and quiet portion of it simply slips out of sight, sinking down into the dark. A moment ago, we ended with the idea of melting ice and flowing water, watching the great glaciers release their frozen grip and send moisture rushing down the mountainsides. Let's pick up that exact thread and follow the water, but not into the roaring rivers or the vast, sunlit oceans. Instead, we are going to follow the water as it quietly, almost invisibly, slips out of sight. When we look at a map of the world, our eyes are naturally drawn to the bright blue lines of winding rivers and the wide, open expanses of lakes and seas. We tend to think of water as something that exists exclusively on top of the earth, a surface feature that we can sail across or swim within. We often think of the ground beneath us as solid, impenetrable rock, a hard boundary that water simply runs across. But the earth is far more welcoming than that. Much of the planet's upper crust is actually porous. It is full of tiny, microscopic, empty spaces, waiting in the dark to be filled. To understand how solid rock can hold an ocean of water, I want you to imagine taking a large, clear glass jar and filling it all the way to the brim with perfectly smooth, round marbles. If you place a lid on the jar, to your eyes, the jar appears completely full. The solid glass marbles take up all the visible space. But if you were to take a pitcher of water and slowly pour it over the top, you would find that you could still pour a surprising amount of water into that full jar. The water gracefully finds its way into the tiny, curved spaces between the marbles, filling the hidden voids. The crust of the earth works in exactly the same way. Whether it is a loose layer of soil in a forest, a deep bed of sand, or even a massive solid layer of sandstone, the earth is full of microscopic voids. When a gentle rain falls on a quiet meadow, not all of that water washes away into the streams. Much of it trickles directly down into the dirt, slipping past the roots of the grass and the trees, moving patiently through the tiny spaces between the grains of sand and the fractures in the solid stone. It soaks into the earth, just as water soaks into a dense, dark sponge. Gravity is the tireless guide here, always pulling the water deeper and deeper into the dark. As a single drop of rain descends, it passes through an upper layer of earth where the microscopic spaces are mostly filled with air. The water is just passing through, sliding down the edges of the soil particles. But eventually, the water reaches a depth where it can go no further. It might hit a layer of dense, unyielding clay or a solid, unfractured bed of granite that simply will not let the water pass. Because the water cannot sink any lower, it begins to pool and accumulate in the porous rock above the barrier. Just like water filling up our jar of marbles from the bottom to the top, the groundwater slowly rises, completely filling every single microscopic crack, pore, and void in the stone. We call this deep, fully soaked region the saturated zone, and the very top of this saturated zone, the invisible line where the dry earth ends and the soaked earth begins, is what we call the water table. Think of the water table not as a perfectly flat, hard surface, but as a gentle, rolling shadow of the landscape resting above it. If you are standing on top of a high hill, the water table might be hundreds of feet below your shoes, resting deep in the dark stone. But if you walk down the hill and step into a low, sweeping valley, the water table is much closer to the surface. Sometimes, in the very lowest parts of a valley, the shape of the land actually dips below the water table. When this happens, the hidden water naturally pools out into the open air, creating a beautiful, quiet wetland, a marsh, or a clear, cold spring. When you see a lone oasis in the middle of a vast, dry desert, you are not looking at a miraculous puddle of rain. You are looking at a place where the wind has carved the sand away so deeply that it has gently scraped the top of the water table, allowing the ancient hidden water to finally see the sun. The water stored in these deep, silent, rocky sponges is called an aquifer. There is a common misconception that an aquifer is a massive, hollow, underground cavern filled with a dark, subterranean lake, like something out of a fantasy novel. But reality is much more subtle, and in many ways, much more beautiful. An aquifer is simply a vast, incredibly thick layer of solid rock, often sandstone or highly fractured limestone, that is completely saturated with fresh water. You could walk right through an aquifer if you were deep underground, but you would be walking through solid, wet stone, not swimming in an open lake. And just like the mantle we explored earlier, this hidden water is not perfectly still. It moves, but it moves at a pace that perfectly matches the deep, slow rhythm of the earth. While a river on the surface might rush toward the sea at several miles an hour, crashing over rocks and carving canyons, the water deep underground is navigating a microscopic, tortuous maze of stone. It must slowly push its way from one tiny pore to the next, filtering patiently through the rock. Because of this immense friction, groundwater might only travel a few inches or a few feet in an entire year. It is a journey of supreme patience. Some of the water resting in the deepest aquifers right now fell as rain thousands, or even tens of thousands of years ago. It is ancient water, a quiet remnant from the last great ice ages, creeping blindly and silently toward the sea in the absolute dark. As it travels, the stone acts as a massive natural filter. The rock slowly strips away impurities, while the water gently dissolves trace amounts of minerals from the stone itself. By the time this water finally emerges from a deep spring, decades or centuries after it first fell from the sky, it is incredibly pure, cold, and heavy with the taste of the earth. These hidden, peaceful reservoirs are the unseen support system for almost all life on the surface. During the long, dry months of summer, when the rains stop falling and the surface streams threaten to dry up, it is the slow, steady, invisible seepage of groundwater into the riverbeds that keeps the water flowing and the forests alive. It is a quiet, enduring sanctuary of moisture, safely tucked away beneath the brittle shell of the world, sustaining us from below. And speaking of life, and the things that the earth cradles in its dark layers, the rocks themselves hold a memory of all the life that has come before us, leading us softly forward into the deep archives of the stone. A moment ago, we ended our exploration of the hidden waters with a promise. I mentioned that as the deep groundwater slowly filters through the stone, it interacts with memories safely tucked away beneath the brittle shell of the world. Let's pick up that exact thread now and look at the quiet echoes preserved in the stone. When we hold a rock in our hand, we naturally think of it as something inherently lifeless. We view geology as the study of the inanimate of minerals, heat, pressure, and cold, empty expanses of time. But the earth is not a barren place, and the stones are not just empty scaffolding. The rocks are the greatest, most patient archives we have. They hold within their dark, heavy layers a perfect, silent memory of almost all the life that has ever come before us. To understand how this happens, we must first appreciate just how incredibly rare and special a fossil truly is. In the normal, everyday cycle of the world, when a living thing finishes its time on Earth, it simply fades away. A tree falls in the forest, and the insects, the fungi, and the damp air gently break it down until it returns completely to the soil. It is a beautiful, necessary part of the cycle, but it leaves no permanent trace. For a living thing to defeat this natural vanishing, for it to be remembered by the stone, it requires a perfect, quiet set of circumstances. It requires a gentle, immediate burial. I want you to imagine a lush, ancient forest, hundreds of millions of years ago, long before the first birds ever took to the sky. The air is warm and heavy. A single, delicate frond from a green fern slowly detaches from its stem. It drifts down through the quiet air and lands softly on the surface of a still, muddy pond. As it becomes waterlogged, it sinks to the very bottom, resting in the soft, dark silt. If it were left out in the open, that leaf would decay in a matter of weeks. But down at the bottom of this quiet pond, the water is stagnant and completely starved of oxygen. The creatures that normally break down fallen leaves cannot survive here. Almost immediately, a new storm brings a fresh layer of fine mud, which gently settles over the leaf, sealing it away in the dark. As the deep time we spoke of earlier begins to pass, the layers of mud pile higher and higher. The immense weight of the earth presses down, squeezing the water out, slowly turning that soft mud into the hard, layered rock we call shale. Deep inside the stone, the pressure and the rising heat cause the delicate organic material of the fern leaf to slowly break down. But because it is trapped, the carbon from the leaf has nowhere to go. It is pressed perfectly flat against the rock. When a geologist eventually splits that piece of shale open, millions of years later, they find a perfect, microscopic, dark film of carbon resting on the pale stone. It looks exactly like a delicate pencil drawing, a perfect shadow of a leaf that fell on a quiet afternoon before humanity was even a thought. This is one way the earth remembers. But there is another way, a method that is even more profound, and it brings us right back to the hidden waters we just finished exploring. Imagine something much larger this time. Picture the heavy, solid bone of a massive dinosaur resting in the coarse sand of an ancient, dried-up riverbed. Just like the leaf, it is quickly buried by a flood of new sand and gravel, protected from the open air. As the centuries pass, the sand slowly turns into porous sandstone. And here is where the ancient groundwater returns to our story. Remember how that hidden water slips patiently through the tiny voids in the rock, moving only a few inches a year? As that ancient water creeps through the sandstone, it completely saturates the buried bone. And remember, too, that this water is heavy with dissolved minerals, silica and calcium gathered from the surrounding stones. Deep in the dark, a microscopic, beautiful exchange begins. As the original organic material of the bone very slowly begins to decay, the groundwater immediately fills the newly empty microscopic spaces with solid minerals. It is a trade, happening one single molecule at a time. The water gently removes a tiny piece of the bone and patiently leaves a tiny piece of solid quartz in its exact place. This process, which geologists call permineralization, is so incredibly precise that it perfectly preserves the internal structure of the object. If you were to look at a slice of this fossilized bone under a microscope, you would still see the intricate, honeycomb-like network of blood vessels and marrow cavities, completely perfectly recreated in solid stone. The shape remains exactly the same, but the material has been entirely replaced. The bone has literally become rock. And the earth does not just preserve the bodies of the things that lived, it preserves the fleeting moments of their lives. We call these trace fossils, and they are perhaps the most hauntingly beautiful echoes of all. Imagine a massive, heavy-set reptile walking slowly across a muddy tidal flat at low tide. Its heavy feet press deep into the wet clay. The sun comes out, baking the mud until it is perfectly hard. The next day, a gentle tide washes in, carrying a different kind of sediment, perhaps a fine, pale sand which fills the footprints without washing away the hardened mud beneath. Over millions of years, the mud and the sand turn to stone. Today, we can peel those layers apart and look at a perfect, three-dimensional cast of a footprint made in a single, passing moment, 150 million years ago. We can find fossilized ripple marks, capturing the exact direction a gentle river was flowing on a Tuesday afternoon in the Jurassic period. We can even find fossilized raindrops, tiny, crater-like impressions in solid stone, marking the exact moment a brief summer shower fell on a muddy beach, long before mammals existed. When you understand this, the world around you takes on a completely different depth. To hold a fossil in the palm of your hand is to physically touch deep time. You are not just holding a piece of cold rock, you are holding a physical bridge across millions of years. You are tracing your finger along the exact ridges of a seashell that once filtered the warm waters of an ocean that has since completely vanished from the map. There is a profound, grounding comfort in this realization. In our daily lives, our own personal histories and anxieties can feel overwhelmingly large. But the fossils remind us that the world has had many faces and many inhabitants. Forests have grown in Antarctica, and vast warm seas have covered the Great Plains of North America. The Earth has patiently carried countless generations of life, giving them a place to stand, and then gently absorbing them back into its heavy, turning layers. Everything belongs. Everything has a place in the stone. And as we gather all these vast, slow, ancient ideas together, we realize that we, too, are simply resting on the surface of this magnificent, continuous story. We have reached the edge of our long journey through the deep, and this quiet realization leads us naturally to our final destination, a place to set these concepts down, let the mind quiet entirely, and rest upon the ancient ground. And so, we come at last to the end of our time with the Earth. This is not an ending, really, but rather a quiet place to pause, a place to rest your mind after traveling across such vast, unimaginable expanses of space and time. You have let these massive, slow, ancient ideas settle beside you as you rested, and they will be here, holding you, whenever you wish to return. We have journeyed far tonight, from the deepest, glowing center of the planet all the way up to the quiet, fossilized echoes of the surface. And now, as your day completely fades and your breathing slows, it is time to gather all of these pieces together, not to memorize them, but simply to feel the weight and the comfort of the world you rest upon. Take a moment to picture the immense, beautiful structure beneath your bed, extending thousands of miles straight down into the dark. At the very center of it all, suspended in the absolute depths, is the solid iron heart of our world. It is a brilliant, white-hot sphere, squeezed into a perfect crystal by the crushing weight of everything above it. It does not rage or boil, it simply hums with a deep, primordial heat. Surrounding that solid heart is the vast, churning ocean of liquid metal, flowing and twisting as the planet spins. You cannot feel it, and you cannot see it, but that swirling iron ocean is quietly projecting a massive, invisible magnetic shield out into space right now, wrapping around the globe and wrapping around the room you are in, keeping the atmosphere safe and the night sky calm. Above that glowing core lies the vast, silent bulk of the mantle. Think of that 2,000-mile thick layer of solid, heavy stone, heated from below until it becomes perfectly flexible. Right now, miles beneath you, massive plumes of warm rock are rising with the deliberate, creeping slowness of a growing oak tree. They are spreading out, cooling, and gently sinking back down into the abyss. It is the slow, heavy breathing of the earth, a continuous, rolling cycle of convection that has been turning for billions of years without ever missing a beat. It is a rhythm so steady, so entirely unhurried, that it demands absolutely nothing from you. You can simply ride upon it, and floating peacefully on top of that moving mantle is the shattered, brittle shell we call home. The tectonic plates, those massive, interlocking puzzle pieces of continental granite and dense ocean basalt, are drifting. As you lie here tonight, the continent you are resting on is moving. It is creeping along at the gentle pace of a growing fingernail, drifting across the globe just as it has since the days of Pangaea. The mountains are very slowly being pushed a fraction of a millimeter higher into the sky, and the deep ocean basins are gently stretching just a little bit wider. The world is reshaping itself in the dark, performing a magnificent, slow-motion dance that you never need to worry about, because it happens on a scale of time that is infinitely larger than our own. You can let go of the names of the rocks and the minerals. You do not need to hold on to the exact process of how magma cools in the dark to form speckled granite, or how the heavy, crushing pressure of a continental collision turns soft shale into sparkling, banded, nice. You only need to hold on to the feeling of the cycle. Remember that the earth wastes nothing. Every grain of sand, every smooth river stone, and every towering cliff is part of a beautiful, endless loop of creation, destruction, and rebirth. The stone is born in the deep fire, it is pushed to the surface, it is gently worn away by the patient rain and the swirling wind. It settles to the bottom of the ocean to become rock once again, and eventually, it is dragged back down into the heat to start over. It is a perfect, closed system. Nothing is ever truly lost. It is only transformed. And as this great wheel turns, it leaves behind a memory. The deep striped layers of sedimentary rock resting beneath the continents hold the history of the world. They hold the fossilized shadows of ancient fern leaves, the preserved footprints of massive creatures that walked across muddy shores millions of years ago, and the microscopic shells of sea life from oceans that dried up long before we arrived. The Earth remembers everything, even the hidden, ancient groundwater, creeping silently through the microscopic pores of the stone deep underground, is a quiet echo of rainstorms that fell thousands of years in the past. The planet is a massive, enduring archive, and you are simply the newest, most beautiful chapter resting gently on its surface. There is a profound, abiding comfort to be found in this perspective. In our daily lives, we are so often caught up in the immediate rush of things. We worry about tomorrow's obligations, the endless lists of tasks, the hurried pace of our careers, and the fleeting anxieties that seem to completely fill our minds. The human world moves so incredibly fast, and it can feel overwhelming, like a frantic current trying to pull us along. But when you lie back and remember the geology of the Earth, you are tuning into a completely different frequency. You are reminded that you are resting on a structure that is billions of years old. The Earth does not care about your deadlines. It does not recognize the arbitrary borders we draw on maps, or the ticking of the clock on your nightstand. It operates entirely on deep time. Against the vast, majestic timeline of the shifting continents and the rising mountains, our daily worries lose their sharp edges. They become small, soft, and entirely manageable. You are allowed to set them down. The world will keep turning, the mantle will keep creeping, and the rivers will keep carving their canyons, whether you worry about them or not. You are not required to hold the world together. The Earth is already doing that for you, with a strength and a patience that is absolutely unbreakable. You don't need to hold on to any of this tightly. There are no tests waiting for you in the morning, no grades to be given, no prerequisites required to simply exist on this planet. You are simply a curious mind, resting on a quiet night, having taken a gentle walk through the deep architecture of the world. I hope you feel a quiet sense that you understand the ground beneath your feet just a little more than you did before, and that this understanding brings you peace. Let your muscles completely relax into the surface beneath you. Feel the steady, reliable pull of gravity gently anchoring you to the crust of the Earth. You are safe here. You are grounded on ancient, steady rock that has survived the fires of the deep and the freezing ice of the surface. It has endured for billions of years, and it is more than strong enough to carry you through the night. Let the slow, deep breathing of the mantle become your own breathing. Let the unhurried, sweeping pace of deep time wash over your thoughts, slowing them down, smoothing out the rough edges of the day, just as a patient river smooths a heavy stone. Until we explore again, let the vast, solid weight of the world carry you. Sleep well, and carry nothing but peace.